Langchain Cohere chat models. Description: the Langchain Cohere chat model provides an easy way to access and use Cohere's large language models (LLMs) for chatbot-like interactions within Langchain applications. Langchain handles the integration and communication with Cohere's APIs, allowing users to leverage powerful AI models for tasks like text generation, summarization, and dialogue management. Inputs. Text: this is the input text that is passed to the Cohere model. It can be a single message or a sequence of messages in a conversation. Temperature: this parameter controls the creativity and randomness of the model's responses. Higher temperatures lead to more unexpected and creative outputs, while lower temperatures result in more predictable and consistent responses. Max tokens: this parameter specifies the maximum number of tokens that the Cohere model should generate in response to a prompt. Outputs. Text: the generated text response from the Cohere model. This can be a single message or a series of messages, depending on the context of the conversation. Metadata: additional information about the Cohere model's response, such as the number of tokens generated and the model's confidence level. Steps. The Langchain wrapper sends the user's input text along with any other relevant parameters like temperature and max tokens to the Cohere API. Cohere's LLM processes the input text, generating a response based on its training data and the provided parameters. The response is then sent back to the Langchain wrapper, where it can be processed further or displayed to the user. Metrics. Perplexity: this measures how well the model predicts the next word in a sequence, with lower values indicating better performance. Blue score: used for evaluating the quality of translation or summarization tasks, comparing generated text to reference outputs. Rouge score evaluates the quality of text summarization by comparing generated summaries to reference summaries. Visualization plots. Attention visualization: visual representation of the model's attention weights during processing, highlighting which words it focuses on. Word embeddings: visualizing how words are represented in the model's internal space, offering insights into semantic relationships. Fine-tune parameters. Learning rate determines the step size for adjusting model parameters during training. Epochs: the number of passes through the entire training dataset during training. Batch size: the number of training examples processed at each step. Uncertainty methods. Temperature scaling: increasing the temperature parameter introduces randomness and provides a measure of uncertainty by exploring different possibilities. Ensemble methods: combining the predictions of multiple Cohere models to improve robustness and reduce uncertainty. Challenges and fixes. Challenge 1: the model might generate responses that are factually incorrect or biased due to limitations in its training data. Sample use case that resulted in challenge 1: when asked about historical events, the model might provide inaccurate information based on biased or incomplete training data. Fixes to challenge 1: carefully curate and select training data to ensure accuracy and diversity. Implement mechanisms for fact-checking and verification during response generation. Provide users with clear disclaimers about potential inaccuracies. Challenge 2: the model might struggle with complex reasoning and logical tasks, leading to nonsensical or illogical responses. Sample use case that resulted in challenge 2: when presented with a complex logical puzzle or a multi-step reasoning task, the model might fail to provide a coherent and logical solution. Fixes to challenge 2: enhance training data with more examples of complex reasoning and logic problems. Explore techniques like symbolic reasoning and graph-based representations to improve logical understanding. Incorporate feedback mechanisms to help the model learn from its mistakes. Challenge 3. The model might be prone to generating repetitive or generic responses. Lacking creativity and diversity. Sample use case that resulted in challenge 3 when asked for a creative story or poem. The model might generate a predictable and unoriginal output. Fixes to challenge 3. Experiment with different prompt formats and use techniques like prompt engineering to encourage creativity. Increase the temperature parameter to introduce randomness and explore a wider range of possibilities. Fine-tune the model on a dataset that emphasizes creativity and originality. Langchain Cohere Chat Models. Chat Cohere. Description. Explain in detail. The Chat Cohere class is a Langchain wrapper around Cohere's Chat API, allowing you to interact with a large language model (LLM) for conversational applications. It allows users to send messages to the model and receive responses. Inputs. Input 1. Explain in detail. Prompt the text input for the model. This is the message the user sends to the LLM. Input 2. Explain in detail. Temperature. A number between 0 and 1. Controlling the creativity of the response. 0 is the most deterministic. 1 is the most creative. Outputs. Output 1. Explain in detail. Text. The text generated by the LLM in response to the user's prompt. Output 2. Explain in detail. Generation info. A dictionary containing additional information about the response, including the LLM model used, the number of tokens, and the generation time. Steps. Step 1. Explain in detail. The Chat Cohere class instantiates a Cohere client using the Cohere API key. Step 2. Explain in detail. When the run method is called, it sends the provided prompt to the Cohere Chat API, using the temperature parameter to control the level of creativity. Step 3. Explain in detail. The API response is processed and returned as a dictionary containing the generated text and additional generation information. Metrics. Metric 1. Explain in detail. The Chat Cohere class does not explicitly define metrics for evaluating its performance. Metric 2. Explain in detail. However, common metrics for evaluating chatbots include perplexity, Blue score, and human evaluation. Visualization plots. Visualization plot 1. Explain in detail. The Chat Cohere class does not provide built-in visualizations. Visualization plot 2. Explain in detail. However, you could visualize the generation process using external libraries like Matplotlib or Seaborn, plotting the tokens generated over time or the probability distribution of different response options. Fine-tune parameters. Parameter 1. Explain in detail. The Chat Cohere class does not offer fine-tuning parameters. Parameter 2. Explain in detail. You can adjust the behavior of the underlying Cohere LLM by changing the temperature parameter, which controls the creativity of the response. Uncertainty methods. Uncertainty method 1. Explain in detail. The Chat Cohere class does not provide built-in uncertainty estimation methods. Uncertainty method 2. Explain in detail. You could implement uncertainty estimation methods by leveraging the Cohere API's capability to return multiple generations or by using techniques like ensemble models or Bayesian inference. Challenges and fixes. Challenge 1. Explain in detail. API key management. Managing API keys securely is crucial for preventing unauthorized access. Sample use case that resulted in challenge 1. An attacker could gain access to your API key and make unauthorized requests to the Cohere API, leading to unexpected costs or data breaches. Fixes to challenge 1. Store the API key securely. Use environment variables or dedicated key management solutions. Limit API key usage. Restrict the scope of the key and use it only when necessary. Monitor API usage, track requests made with the API key to detect any unusual activity. Challenge 2. Explain in detail handling long conversations, maintaining context and consistency. Over long conversational exchanges can be challenging. Sample use case that resulted in challenge 2 in a long dialogue. The LLM might forget previous turns or make inconsistent statements. Fixes to challenge 2. Implement a memory system, store relevant information from previous turns and make it available to the LLM. Use a context window, provide the LLM with a window of previous conversation history to ensure it has access to the relevant context. Experiment with different conversation strategies. Consider techniques like dialogue act tracking or discourse analysis. YAML. Langchain Cohere chat models get Cohere chat request. Description: this method constructs a Cohere chat request object to be used with the Cohere API for conversational interactions. Inputs: prompt a string containing the user's message or query to be sent to the chat model. This is the input that initiates the conversation. History: an optional list of tuples, each containing the user's message and the model's response from previous turns in the conversation. This provides context for the current interaction. Temperature: a float value between 0 and 1 that controls the randomness of the model's responses. Higher temperatures result in more diverse and creative outputs, while lower temperatures produce more predictable responses. Max tokens: an integer specifying the maximum number of tokens the model should generate in its response. This limits the length of the generated text. Stop sequences: an optional list of strings that indicate the end of the conversation. When the model encounters any of these sequences, it will stop generating text. Outputs: response: a dictionary containing the model's response to the input prompt. This includes the generated text, information about the conversation, and other relevant details. Error: an optional string indicating any errors encountered during the request processing. Steps: the method takes the user's prompt and optional history as input. It constructs a request object for the Cohere API, including the prompt, history, and other parameters like temperature, max tokens, and stop sequences. The method sends this request to the Cohere API and receives a response. It parses the response and extracts the generated text and other relevant information. Metrics: response quality evaluates the relevance, coherence, and fluency of the generated text. Conversation consistency assesses how well the model maintains context and consistency across multiple turns in the conversation. Latency measures the time taken by the Cohere API to process the request and generate a response. Visualization plots: conversation flow: a visual representation of the conversation history, showing the user's inputs and the model's responses. Response length distribution: a plot showing the distribution of the number of tokens generated by the model in different turns. Fine-tune parameters: temperature influences the randomness of the model's responses. Max tokens limits the length of the generated text. Stop sequences controls when the model should stop generating text. Uncertainty methods: confidence scores: the model can provide confidence scores for each generated token, indicating its uncertainty about the prediction. Alternative responses: the API can return multiple candidate responses, providing insights into the model's uncertainty. Challenges and fixes. Challenge 1: handling ambiguous or contextually unclear prompts. Sample use case that resulted in challenge 1: a user provides a prompt that can be interpreted in multiple ways, leading to a confusing or irrelevant response. Fixes to challenge 1: implement techniques to resolve ambiguity. such as using context from previous turns or asking for clarification from the user. Use prompt engineering to structure the prompt more clearly and explicitly. Explore different models or fine-tuning strategies that are better suited for handling ambiguity. Challenge 2: Maintaining context and consistency over long conversations. Sample use case that resulted in challenge 2 after several turns. The model may forget previous information or generate responses that are inconsistent with the conversation history. Fixes to challenge 2. Use memory mechanisms to store and retrieve information from previous turns. Implement techniques like attention mechanisms to focus the model's attention on relevant context. Experiment with different conversation management strategies, such as using a dialogue state tracker. YAML. Langchain Cohere chat models get role. Description: explain in detail. This method retrieves the role of a specific Cohere chat model. The role defines the model's intended use and potential capabilities. Inputs. Input 1: explain in detail model name, the name of the Cohere chat model you want to retrieve. Hey. Role 4. This is typically a string identifier. E.g. command xlarge20230516. Outputs. Output 1: explain in detail role, the role of the specified Cohere chat model. This is a string describing the intended use and potential capabilities. E.g. conversational. Steps. Step 1: explain in detail. The getRole method internally interacts with the Cohere API to fetch the model metadata, which includes the role. Metrics. Metric 1: explain in detail, not applicable for this method as it simply retrieves existing information. Visualization plots. Visualization plot 1: explain in detail, not applicable for this method. Fine-tune parameters. Parameter 1: explain in detail, not applicable for this method. Uncertainty methods. Uncertainty method 1: explain in detail, not applicable for this method. Challenges and fixes. Challenge 1: explain in detail, invalid model name. Sample use case that resulted in challenge 1, providing a non-existent or incorrectly formatted model name. Fixes to challenge 1: ensure the model name is correct and matches the available Cohere models. Challenge 2: explain in detail API connection errors. Sample use case that resulted in challenge 2: issues with internet connectivity or API access. Fixes to challenge 2: verify network connection. Check API credentials and quotas. Or contact Cohere support for assistance. Langchain Cohere agent. Description: explain in detail. The Cohere agent is a powerful tool for building conversational AI. Agents powered by Cohere's large language models (LLMs). It leverages Langchain's framework to allow for seamless integration with external tools and data sources, making it ideal for complex tasks that require knowledge and reasoning. Inputs. Input 1: explain in detail. The primary input is a user prompt or query. This can be a simple question, a command, or a more complex request. The agent analyzes the input to understand the user's intent. Input 2: explain in detail. Additional inputs might include context, previous conversations, or relevant background information. Tools, specific tools or APIs that the agent can interact with to get information or perform actions. Outputs. Output 1: explain in detail the agent's response to the user's input. This can be a textual response, a generated piece of content, or a series of actions performed based on the user's request. Output 2: explain in detail. Depending on the task and configuration, the agent might also output intermediate results. If the agent performs multiple steps, it might share intermediate results with the user. Error messages: if the agent encounters issues or cannot fulfill the request, it might provide an error message. Steps. Step 1. Explain in detail. The agent receives the user's input and analyzes it to understand the intent. This might involve parsing the text, identifying keywords, and understanding the context of the conversation. Step 2. Explain in detail. Based on the understood intent, the agent decides on a course of action. This might involve retrieving information from external sources, calling APIs or external tools, generating text, code, or other creative outputs, performing actions in the real world. Metrics. Metric 1. Explain in detail accuracy of the agent's responses. This can be measured by comparing the generated output to a ground truth or by evaluating the agent's ability to fulfill the user's request. Metric 2. Explain in detail efficiency of the agent's operations. This can be measured by the time taken to process the user's input and generate a response. Visualization plots. Visualization plot 1. Explain in detail flowcharts or diagrams representing the agent's workflow and decision-making process. Visualization plot 2. Explain in detail visualizations of the agent's knowledge base or data sources, allowing for easier understanding of the context and information used. Fine-tune parameters. Parameter 1. Explain in detail model parameters influencing the agent's behavior and responses. For example, adjusting parameters related to creativity, tone, or specific knowledge domains. Parameter 2. Explain in detail parameters for controlling the interaction with external tools, such as setting limits on the number of API calls or defining the scope of allowed actions. Uncertainty methods. Uncertainty method 1. Explain in detail techniques for measuring and communicating the agent's confidence in its responses. This could involve using probability distributions or providing confidence scores for generated outputs. Uncertainty method 2. Explain in detail methods for incorporating uncertainty into the agent's decision-making process, such as exploring multiple possibilities or suggesting alternative solutions when faced with ambiguity. Challenges and fixes. Challenge 1. Explain in detail handling ambiguous user inputs. Sample use case that resulted in challenge 1. A user might ask a question that can be interpreted in multiple ways, leading to the agent providing an incorrect or irrelevant response. Fixes to challenge 1. Clarifying questions. The agent could ask the user for more information to clarify the intent. Providing multiple options. The agent could present multiple interpretations of the user's request and ask the user to choose the correct one. Challenge 2. Explain in detail ensuring the agent's responses are factually accurate. Sample use case that resulted in challenge 2. The agent might access outdated or incorrect information from external sources, leading to inaccurate responses. Fixes to challenge 2. Verifying information. The agent could cross-reference information from multiple sources to ensure accuracy. Using trusted sources. The agent could be trained to rely on specific, highly reputable sources for information. Challenge 3. Explain in detail preventing the agent from generating biased or harmful content. Sample use case that resulted in challenge 3. The agent might generate offensive or discriminatory language based on its training data. Fixes to challenge 3. Implementing safety filters. The agent could be equipped with filters to detect and prevent the generation of harmful content. Fine-tuning for ethical behavior. The agent could be fine-tuned on data that promotes fairness and inclusivity. Langchain Cohere agent. Create Cohere tools agent. Description. Explain in detail the Create Cohere tools agent function from the Langchain Cohere library. Is used to construct the specialized agent that leverages the capabilities of the Cohere API for tasks involving language processing and generation. This agent is built upon the Langchain framework and empowers users to seamlessly integrate Cohere's powerful language models into their applications. Inputs. Input 1. Explain in detail. The Create Cohere Tools agent function accepts a set of input parameters, including the desired Cohere model, e.g., command extra large nightly, the tools to be used by the agent, e.g., a list of Langchain tools like LLM chain, function tool, or custom tools, the prompt template used to guide the agent's interaction with the tools, e.g., a template defining how the agent should request tool usage, and optional parameters like the maximum number of steps the agent should take and the verbose logging level. Input 2. Explain in detail. A prompt template is used to guide the agent's interaction with the tools. This template is a string defining how the agent should request tool usage. It can include placeholders for information that is dynamically filled in during the agent's execution. Outputs. Output 1. Explain in detail. The Create Cohere Tools agent function returns a Cohere-powered agent object. This agent is capable of using the specified tools in conjunction with the Cohere model to perform tasks as instructed by the user. Output 2. Explain in detail. The agent's output will vary depending on the task it is performing. It can be a string of text, a structured output like a JSON object, or any other format that is relevant to the task at hand. Steps. Step 1. Explain in detail. The function initializes the Cohere model specified by the user. This involves establishing a connection to the Cohere API and loading the desired model. Step 2. Explain in detail. The function creates a Langchain agent using the specified tools in the prompt template. This involves defining the agent's actions, including how it should interact with the tools based on the prompt template. Step 3. Explain in detail. The function combines the Cohere model with the agent to create a complete Cohere-powered agent. This agent can now perform tasks by leveraging both the model's language capabilities and the functionality of the provided tools. Metrics. Metric 1. Explain in detail. The performance of the Cohere-powered agent can be evaluated using various metrics, including the accuracy of the generated output, the speed of execution, and the fluency of the generated text. Metric 2. Explain in detail for tasks involving language generation. Metrics like perplexity and blue score can be used to measure the quality of the output. Visualization plots. Visualization plot 1. Explain in detail. Depending on the task, the output of the agent can be visualized using various plots. For example, if the agent is generating text, a histogram of word frequencies can be plotted to analyze the distribution of words in the output. Visualization plot 2. Explain in detail for tasks involving classification or regression. Scatter plots and bar charts can be used to visualize the agent's performance. Fine-tune parameters. Parameter 1. Explain in detail. The Create Cohere Tools agent function allows users to fine-tune various parameters of the agent, including the maximum number of steps the agent should take and the verbose logging level. Parameter 2. Explain in detail. The temperature parameter of the Cohere model can be adjusted to control the creativity and randomness of the generated output. A higher temperature will result in more creative and unexpected outputs, while a lower temperature will produce more predictable and coherent outputs. Uncertainty methods. Uncertainty method 1. Explain in detail. There are several methods for quantifying uncertainty in the agent's output, including techniques like Bayesian inference and confidence intervals. Uncertainty method 2. Explain in detail for tasks involving language generation. Perplexity can be used as a proxy for uncertainty. with lower perplexity values indicating higher confidence in the generated text. Challenges and fixes. Challenge 1. Explain in detail. One challenge that can arise when using Cohere-powered agents is the potential for the agent to become stuck in a loop, repeating the same actions without making progress towards the desired outcome. Sample use case that resulted in challenge 1. A user might provide a prompt that leads the agent to continually request the same information from a tool, resulting in an endless loop. Fixes to challenge 1. To mitigate this challenge, the user can implement a mechanism to track the agent's progress and terminate execution if the agent is not making sufficient progress. Another approach is to carefully design the prompt template to guide the agent towards a successful completion of the task. Challenge 2. Explain in detail. The agent might generate outputs that are factually incorrect or do not align with the desired context. Sample use case that resulted in challenge 2. An agent tasked with summarizing a news article might misinterpret certain information or present biased information. Fixes to challenge 2. To address this challenge, it is crucial to provide the agent with accurate and comprehensive context. This can involve pre-processing the input data to remove biases or providing the agent with additional information that is relevant to the task. Additionally, incorporating techniques like knowledge grounding can help the agent access external knowledge sources to verify information and ensure accuracy. Challenge 3. Explain in detail. The Cohere API might encounter errors or timeouts, leading to interruptions in the agent's execution. Sample use case that resulted in challenge 3. During peak usage, the Cohere API might experience high latency or become temporarily unavailable, causing the agent's execution to stall. Fixes to challenge 3. To handle these situations, it is important to implement error handling mechanisms in the agent. This can involve retries, exponential backoff strategies, or using alternative APIs or models if the Cohere API is unavailable. Langchain Cohere Common description. Explain in detail. The Langchain Cohere Common component is a wrapper for the Cohere API. Within the Langchain framework, it allows developers to easily leverage Cohere's powerful language models for tasks like text generation, summarization, translation, and more. Inputs. Input 1. Explain in detail. Text input to be processed by the Cohere model. This can be a string, list of strings, or any other format that can be converted to text. Input 2. Explain in detail optional parameters for configuring the Cohere model, such as the model name, temperature, maximum length, etc. Outputs. Output 1. Explain in detail the generated text output from the Cohere model. This can be a single string, a list of strings, or any other format depending on the specific task. Output 2. Explain in detail optional output, such as the model's response metadata, including timestamps, token counts, etc. Steps. Step 1. Explain in detail. The Langchain Cohere component takes the input text and any specified parameters. Step 2. Explain in detail. It sends a request to the Cohere API using the specified model and parameters. Step 3. Explain in detail. The component receives the response from Cohere, which contains the generated text and any relevant metadata. Metrics. Metric 1. Explain in detail accuracy. This can be measured using metrics like blue, rouge, or other task-specific metrics, depending on the desired output. Metric 2. Explain in detail latency. This metric measures the time taken for the Cohere model to generate the response, which is important for real-time applications. Visualization plots. Visualization plot 1. Explain in detail. Performance graphs can be generated to track accuracy and Latency over time. Providing insights into model performance and potential issues. Visualization plot to explain in detail. Distribution plots can be used to visualize the frequency of different generated words or phrases, which can be helpful for understanding the model's output patterns. Fine-tune parameters. Parameter 1. Explain in detail. The model parameter allows you to select a specific Cohere model, such as command or generate, each having different strengths and weaknesses. Parameter 2. Explain in detail. The temperature parameter controls the creativity and randomness of the generated text. A higher temperature leads to more unexpected outputs. Uncertainty methods. Uncertainty method 1. Explain in detail. Cohere itself doesn't offer built-in uncertainty measures. However, you can implement external techniques like Monte Carlo simulations or dropout-based methods to estimate uncertainty in the generated text. Uncertainty method 2. Explain in detail. Use confidence scores provided by Cohere if available to understand the model's certainty about generated text. These scores can be used to identify potential areas where the model may be less confident or require further analysis. Challenges and fixes. Challenge 1. Explain in detail. API rate limiting. Cohere API has rate limits to prevent overuse. Sample use case that resulted in challenge 1. Making too many requests in a short period can trigger rate limiting. Fixes to challenge 1. Use a retry strategy to automatically retry requests that fail due to rate limiting. Implement a rate limiting mechanism to throttle requests. Use Cohere's quota information to monitor API usage and adjust request frequency accordingly. Challenge 2. Explain in detail model performance issues. The chosen Cohere model may not perform well for a specific task. Sample use case that resulted in challenge 2. The command model may not be suitable for creative text generation. Fixes to challenge 2. Experiment with different Cohere models to find one that best suits the specific task. Fine-tune the chosen Cohere model on a relevant dataset to improve its performance for the given task. Use a different language model altogether if necessary. Langchain Cohere. Common Cohere citation. Description. Cohere citation is a Langchain tool that leverages the Cohere API to retrieve citations for a given text. It generates citations by identifying key phrases and concepts in the text and then using a Cohere API to search for relevant sources. Inputs. Text. The text for which to generate citations. This should be a string containing the text. Outputs. Citations. A list of citations generated from the text. Each citation is a dictionary with the following keys. URL. The URL of the source. Title. The title of the source. Author. The authors of the source. Publication date. The publication date of the source. Steps. The tool extracts key phrases and concepts from the input text. It uses the Cohere API to search for relevant sources based on these phrases and concepts. The tool retrieves the citations for the retrieved sources. It returns the list of citations. Metrics. Citation accuracy. This metric measures the percentage of citations that are relevant and accurate to the input text. Coverage. This metric measures the percentage of key concepts and phrases in the text that are covered by the generated citations. Visualization plots. Citation density plot. This plot shows the distribution of citations across the input text. This can be useful for identifying areas where more citations are needed. Fine-tune parameters. Model. The Cohere model used to generate the citations. There are various models available, each with different strengths and weaknesses. Query length. The maximum length of the query sent to the Cohere API. Longer queries can retrieve more comprehensive results but may take longer to process. Number of citations, the maximum number of citations to return. Uncertainty methods. Confidence score, the Cohere API can return a confidence score for each retrieved citation. This score indicates how confident the API is that the citation is relevant to the input text. Citation diversity, this method measures the diversity of the retrieved citations. A diverse set of citations suggests that the tool has covered a wide range of relevant sources. Challenges and fixes. Challenge 1. The tool may generate citations that are not relevant to the input text. Sample use case: when the input text contains complex or ambiguous concepts, the tool may misinterpret the text and generate irrelevant citations. Fixes. Try using different Cohere models with different strengths and weaknesses. Adjust the query length parameter to ensure that the API has enough information to understand the input text. Carefully review the generated citations and manually remove any that are not relevant. Challenge 2. The tool may fail to identify all key concepts and phrases in the input text. Sample use case: when the input text is very short or lacks clear concepts, the tool may not be able to generate a comprehensive set of citations. Fixes. Provide more context in the input text by including background information are relevant. Definitions. Use a more advanced text summarization technique to extract key concepts and phrases. Manually add citations for any missing concepts. Challenge 3. The tool may generate duplicate citations. Sample use case: when the input text contains multiple references to the same source, the tool may generate duplicate citations. Fixes. Use a deduplication algorithm to identify and remove duplicate citations. Manually review the generated citations and remove any duplicates. Langchain Cohere embeddings. Description: explain in detail. The Langchain Cohere embeddings module leverages Cohere's powerful embedding models to transform text into numerical representations, embeddings that capture semantic meaning. These embeddings can be used for tasks like text similarity comparisons, clustering documents, and building recommendation systems. Inputs. Input 1. Explain in detail text. The input to the embedding model is text. This can be a single sentence, a paragraph, or a full document. Input 2. Explain in detail model. You specify the Cohere embedding model you want to use. Cohere offers various models, each with different strengths and limitations. Outputs. Output 1. Explain in detail embeddings. The output is a numerical representation of the input text. The dimensionality of the embedding vector depends on the chosen Cohere model. Output 2. Explain in detail metadata depending on the specific embedding model. Additional metadata might be returned alongside the embeddings, such as information about the model used. Steps. Step 1. Explain in detail text preprocessing. The input text is typically cleaned and preprocessed to remove irrelevant information, such as punctuation and stop words. Step 2. Explain in detail embedding generation. The preprocessed text is fed into the Cohere embedding model, which generates the numerical embedding vector. Metrics. Metric 1. Explain in detail cosine similarity measures the similarity between two embedding vectors. A higher cosine similarity value indicates a greater semantic similarity between the corresponding texts. Metric 2. Explain in detail Euclidean distance calculates the distance between two embedding vectors. A smaller Euclidean distance implies greater similarity between the texts. Visualization plots. Visualization plot 1. Explain in detail scatter plots. Embeddings can be visualized using scatter plots, where each data point represents a text document, and the positions are determined by the embedding coordinates. This helps to identify clusters or relationships between texts. Visualization plot to explain in detail tsna. T-distributed stochastic neighbor embedding tsna is a dimensionality reduction technique that can be used to visualize high-dimensional embeddings in a lower dimensional space. Fine-tune parameters. Parameter 1. Explain in detail model selection, choosing the appropriate Cohere embedding model for the specific task and data is crucial. Different models might perform better for different types of text or applications. Parameter 2. Explain in detail preprocessing options. The specific preprocessing steps applied to the text can significantly impact the quality of the embeddings. Experimenting with different techniques, such as stemming or lemmatization, might be necessary. Uncertainty methods. Uncertainty method 1. Explain in detail dropout. Applying dropout during the embedding generation process can introduce randomness and provide an estimate of uncertainty in the embeddings. Uncertainty method 2. Explain in detail ensemble methods, using multiple Cohere embedding models and combining their predictions can help reduce uncertainty and improve robustness. Challenges and fixes. Challenge 1. Explain in detail model bias. Cohere embedding models, like any machine learning model, can exhibit bias based on the data they were trained on. This bias might lead to unfair or inaccurate results. Sample use case that resulted in challenge 1. A text embedding model trained on a dataset with a disproportionate representation of a particular gender might generate biased embeddings for texts related to that gender. Fixes to challenge 1. Carefully curate and diversify the training data to reduce bias. Implement fairness metrics and analysis techniques to identify and mitigate bias in embeddings. Challenge 2. Explain in detail data quality. The quality of the input text data directly affects the quality of the embeddings. Noise, inconsistencies, or errors in the data can lead to inaccurate or unreliable results. Sample use case that resulted in challenge 2. A dataset containing spelling errors or inconsistencies in text formatting can lead to incorrect embeddings. Fixes to challenge 2. Pre-process the input data to correct errors, inconsistencies, and noise. Consider using robust embedding models that are less sensitive to noise in the data. Langchain Cohere embeddings. Cohere embeddings. Description. Cohere embeddings is a Langchain embedding class that utilizes Cohere's embedding API to generate vector representations of text. Cohere offers a powerful embedding model capable of understanding semantic relationships within text. Inputs. Text: a string containing the text you want to embed. Outputs. Embeddings: a list of floating point numbers representing the embedded vector for the input text. Steps. The Cohere embeddings class takes the input text. It sends a request to the Cohere API, specifying the text and the desired embedding model. Cohere's server processes the text and generates a dense vector representation. The resulting vector is returned to Langchain as a list of floats. Metrics. Similarity score: the dot product of two embedded vectors can be used to estimate the semantic similarity between the corresponding texts. Visualization plots. Dimensionality reduction techniques like PCA or tsna can be applied to the embedded vectors to visualize the relationships between different texts in a lower dimensional space. Fine-tune parameters. Model specifies the Cohere embedding model to use. Different models offer varying levels of performance and are suited for different tasks. Model type allows you to choose between text embedding ADA002 or text embedding ADA001. Cohere API key or API key for accessing Cohere's services. Uncertainty methods. Probabilistic embeddings. Some embedding models offer the option to obtain a probability distribution over the embedding space. providing a measure of uncertainty. Challenges and fixes. Challenge 1: API rate limiting. Sample use case that resulted in Challenge 1: sending a large number of embedding requests in a short period might trigger Cohere's rate limiting. Fixes to Challenge 1: implement a rate limiter to control the frequency of requests. Consider using a batching approach to process multiple texts together. Challenge 2: model choice. Sample use case that resulted in Challenge 2: choosing an inappropriate embedding model for your specific task can lead to suboptimal results. Fixes to Challenge 2: experiment with different Cohere models to determine which one is best suited for your task. Consider factors such as the size and complexity of the text and the desired semantic relationships. Langchain Cohere LLMs. Description: explain in detail. The Langchain Cohere LLM is a wrapper for the Cohere API. It allows you to utilize Cohere's powerful language models directly within your Langchain. Applications. Inputs. Input 1: explain in detail text prompt. This is the input text you provide to the LLM. It can be anything from a simple question to a more complex story or instruction. Input 2: explain in detail API key. This is your Cohere API key, which you need to provide to authenticate your requests and access the LLM's capabilities. Outputs. Output 1: explain in detail text response. The LLM processes your prompt and generates a text-based output in response. This could be a coherent answer to your question, a story continuation, or any other text-based output based on the input. Output 2: explain in detail model prediction. Depending on the specific task, the output might include structured data like probabilities, classifications, or other model predictions. Steps. Step 1: explain in detail prompt formulation. You begin by crafting a clear and concise text prompt that accurately reflects the information or task you want the LLM to handle. Step 2: explain in detail API request. Langchain sends your prompt and your Cohere API key to the Cohere API endpoint. Step 3: explain in detail model processing. The Cohere LLM processes your prompt and generates a response based on its training data and the specific model you are using. Step 4: explain in detail response parsing. Langchain receives the response from the Cohere API and formats it into a consistent output structure. Metrics. Metric 1: explain in detail model accuracy. This metric assesses how well the LLM accurately answers questions or performs the intended tasks. It might be evaluated based on benchmarks, human evaluations, or task-specific metrics. Metric 2: explain in detail response quality. Measures the clarity, coherence, and relevance of the LLM's output. This might involve evaluating factors like grammatical correctness, logical flow, and the overall quality of the generated text. Visualization plots. Visualization plot 1: explain in detail model performance. Visualize the LLM's accuracy or quality over time, different inputs, or various model parameters. This can help track improvement and identify areas for optimization. Visualization plot 2: explain in detail prompt length vs response time. Explore the relationship between the length of the prompt and the time it takes for the model to generate a response. This helps understand resource consumption and potential bottlenecks. Fine-tune parameters. Parameter 1: explain in detail model type. Choose from different Cohere models, e.g. command, generate, etc., based on your specific requirements for text generation, summarization, or other tasks. Parameter 2: explain in detail temperature. Adjust the creativity and randomness of the LLM's responses. Higher temperatures encourage more diverse and unexpected outputs. while lower temperatures produce more predictable and focused results. Uncertainty methods. Uncertainty method 1. Explain in detail confidence scores. Cohere's API might provide confidence scores associated with the LLM's predictions. These scores indicate the model's level of certainty about its outputs. Uncertainty method 2. Explain in detail. Ensemble methods use multiple models or different parameters to generate a consensus response. The spread in the responses can indicate uncertainty. Challenges and fixes. Challenge 1. Explain in detail API key management. Managing and securing API keys in a production environment is crucial. Sample use case that resulted in challenge 1. Exposing the API key within client-side code. Insecure storage can lead to unauthorized access. Fixes to challenge 1. Use environment variables to store sensitive data. Employ secure API key storage solutions like HashiCorp Vault or AWS Secrets Manager. Challenge 2. Explain in detail response length and time. LLMs can generate lengthy responses, and the response generation process might take time. Sample use case that resulted in challenge 2. Long prompts or complex tasks might lead to extended response times or lengthy text outputs that exceed desired limits. Fixes to challenge 2. Implement response length limits and timeouts. Consider using prompt engineering techniques to improve response efficiency. Challenge 3. Explain in detail cost optimization. Cohere API calls can incur costs based on usage. Sample use case that resulted in challenge 3. Running frequent or resource-intensive LLM requests can lead to substantial costs. Fixes to challenge 3. Use caching mechanisms to store and reuse responses for frequently asked prompts. Optimize prompt formulations to reduce model processing time. Challenge 4. Explain in detail model bias. LLMs trained on large datasets might exhibit biases present in the training data. Sample use case that resulted in challenge 4. The LLM might generate responses that perpetuate harmful stereotypes or biases. Fixes to challenge 4. Choose models that have been specifically designed for fairness and bias mitigation. Implement post-processing techniques to detect and mitigate biased outputs. Langchain Cohere LLMs base Cohere. Description: the base Cohere class provides a Langchain interface to the Cohere API, enabling you to use Cohere models for various natural language processing tasks. Inputs. Prompt the input text or question to be processed by the Cohere model. It can be a string or a list of strings for batch processing. Model: the name of the Cohere model to use. Defaults to command extra large nightly if not specified. Temperature: a value between 0 and 1 controlling the randomness of the model's output. Higher values lead to more diverse and creative responses. Defaults to 0.7. Max tokens: the maximum number of tokens to generate. Defaults to 256. Top controls the probability distribution of the model's output. It limits the probability of the next token to a specified percentage. Defaults to 0.95. Top: similar to top, but instead of probability, it limits the number of tokens considered for the next prediction. Defaults to 50. Outputs. Text: the generated text output by the Cohere model based on the provided prompt and parameters. Steps. The base Cohere class sends the prompt and parameters to the Cohere API. The Cohere API processes the input using the specified model and returns the generated text. Metrics. Coherence measures the overall quality and flow of the generated text. Fluency evaluates the grammatical correctness and readability of the output. Relevance assesses how well the generated text aligns with the input prompt. Visualization plots. Token distribution shows the frequency of different tokens in the generated text. Attention weights visualizes the attention mechanism used by the model, highlighting the words or phrases that influenced the prediction. Fine-tune parameters. Learning rate, the rate at which the model's weights are updated during training. Epochs, the number of times the training dataset is processed during fine-tuning. Batch size, the number of training examples processed in one iteration. Uncertainty methods. Temperature scaling adjusts the temperature parameter to control the randomness of the models. Output. Higher temperatures lead to more uncertain responses. Challenges and fixes. Challenge 1, the model may generate text that is factually incorrect or biased. Sample use case that resulted in challenge 1, asking the model to generate a summary of a historical event with known inaccuracies. Fixes to challenge 1. Fine-tune the model on a dataset with accurate and balanced information. Use prompt engineering techniques to guide the model towards providing unbiased and reliable outputs. Integrate external fact-checking mechanisms to verify the generated text. Challenge 2, the model may struggle to handle complex or nuanced prompts. Sample use case that resulted in challenge 2, asking the model to provide an in-depth analysis of a philosophical concept. Fixes to challenge 2. Provide more context and background information in the prompt. Use prompt engineering techniques to break down complex prompts into simpler sub-questions. Consider using a more powerful or specialized model that is better equipped to handle complex prompts. Challenge 3, the generated text may not be relevant or coherent. Sample use case that resulted in challenge 3, asking the model to generate a creative story with a specific theme, but the output deviates from the requested theme. Fixes to challenge 3. Improve the prompt clarity and specificity to better guide the model's generation. Experiment with different model parameters, such as temperature and top, to influence the coherence and relevance of the output. Consider using techniques like prompt chaining or iterative refinement to improve the coherence and relevance of the generated text. Langchain Cohere LLMs. Cohere. Description. Cohere is a large language model LLM specifically designed for natural language processing (NLP) tasks. It's a powerful tool for generating creative text, translating languages, summarizing information, and much more. Inputs. Text. The text input to the LLM. This can be a question, a prompt, a piece of text to summarize, or any other type of text. Outputs. Text. The output text generated by the LLM based on the provided input. This can be an answer, a response, a summary, a translation, or any other type of text relevant to the input. Steps. The Cohere LLM processes the input text. It analyzes the text and applies its internal knowledge and training to generate an appropriate output. Metrics. Accuracy. How well the LLM's output matches the expected or desired result based on the input. Fluency. The quality and coherence of the generated text. Relevance. How relevant the output text is to the input text. Visualization plots. Now, fine-tune parameters. Model the specific Cohere model to use for the task. Temperature controls the creativity and randomness of the output. Higher temperature leads to more creative outputs. Max tokens limits the maximum number of tokens the LLM will generate. Top filters the probability distribution of possible outputs, choosing only the top k most probable tokens. Uncertainty methods. Now, challenges and fixes. Challenge 1, generating inaccurate or irrelevant responses. Sample use case that resulted in challenge 1, providing a vague or ambiguous prompt. Fixes to challenge 1, provide more specific and detailed prompts to guide the LLM. Use examples to clarify expectations. Challenge 2, generating repetitive or nonsensical output. Sample use case that resulted in challenge 2 using a low temperature parameter, leading to less creative and potentially repetitive output. Fixes to challenge 2: increase the temperature parameter to encourage more diversity and creativity. Try different model variations. Challenge 3: output exceeding the token limit. Sample use case that resulted in challenge 3 setting a low maximum token limit, resulting in truncated output. Fixes to challenge 3: increase the maximum token limit to allow for longer outputs. Use techniques like summarization or truncation to shorten the output if necessary. Challenge 4: output not matching the desired style or tone. Sample use case that resulted in challenge 4: input text does not clearly specify the desired style or tone. Fixes to challenge 4: use prompts that explicitly set the desired style or tone. Provide examples of the desired style or tone. Langchain Cohere LLMSA completion with retry. Description: this tool utilizes the Cohere API to generate text completions with a retry mechanism, improving the robustness of text generation by handling potential errors. Inputs. Prompt the input text that serves as the context for the completion. This could be a sentence, paragraph, or even a larger document. Max tokens: the maximum number of tokens the model is allowed to generate. This parameter controls the length of the generated text. Temperature controls the creativity and randomness of the generated text. Higher values produce more diverse and unpredictable completions. Top a probability threshold for the sampling process. The model only considers tokens with a probability higher than this threshold, resulting in more predictable outputs. Top the number of top candidates to consider for sampling. Similar to top, this parameter influences the randomness of the generated text. N the number of different completions to generate for the same input prompt. This allows for exploring different possible continuations of the text. Stop sequences: a list of strings that, if encountered during generation, will signal the model to stop generating further text. Outputs. Generated text: the text generated by the model in response to the input prompt. It represents the completed continuation of the input text. Status indicates the success or failure of the text generation process. This can be useful for debugging and understanding the performance of the tool. Steps. The tool first sends a request to the Cohere API using the provided input parameters. If the request is successful, the generated text is returned as the output. If the request fails, the tool attempts to retry the request multiple times before giving up. Metrics. Generation time: the time taken to complete the text generation process. Number of retries: the number of times the request was retried before successfully generating text. Visualization plots. Completion length distribution: a histogram showing the distribution of the length of a generated text for different input prompts. Retry rate: a bar chart showing the percentage of requests that required retries for different input prompts. Fine-tune parameters. Model name: the specific Cohere language model to be used for text generation. Different models may have different strengths and weaknesses. Retry attempts: the maximum number of times the tool will attempt to retry a failed request. Retry delay: the delay between consecutive retries, allowing for the API to potentially recover from temporary errors. Uncertainty methods. None. Challenges and fixes. Challenge 1: network connectivity issues can cause the request to fail. Sample use case that resulted in challenge 1: the user is connected to a weak internet connection, leading to intermittent connectivity. Fixes to challenge 1: implement a retry mechanism to handle temporary network issues. The retry mechanism should include a delay between attempts and a maximum number of retries. Challenge 2. The Cohere API may be temporarily unavailable due to maintenance or other reasons. Sample use case that resulted in Challenge 2. The Cohere API is undergoing scheduled maintenance, resulting in a temporary outage. Fixes to Challenge 2. Implement the retry mechanism with a delay between attempts. The retry mechanism should also include a maximum number of retries and a fallback mechanism in case the API remains unavailable. Challenge 3. The Cohere API may return an error due to invalid input parameters or an unexpected error condition. Sample use case that resulted in Challenge 3. The user provides invalid input parameters, such as an invalid model name or a prompt that is too long. Fixes to Challenge 3. Validate the input parameters before sending the request to the API. Implement a retry mechanism with a delay between attempts for unexpected errors. Langchain Cohere LLMS completion with retry. Description: the completion with retry method from the Langchain Cohere LLM is designed to handle. Langchain Cohere LLMS enforces stop tokens. Description: this parameter controls whether Cohere's model will stop generating text at the specified stop sequence. This is helpful for ensuring that the model does not continue generating text beyond a certain point, such as when it has reached a certain length or has encountered a particular word or phrase. Inputs. Prompt: the text prompt that is provided to the Cohere model. Stop sequences: a list of strings that indicate the stop sequences that should be used. Outputs. Generated text: the text generated by the Cohere model. Steps. The Cohere model is provided with the input prompt. The model begins generating text. If the model encounters any of the stop sequences specified in the stop sequences parameter, it will stop generating text. The generated text is returned to the user. Metrics. Generation quality: the quality of the generated text, measured by metrics such as fluency, coherence, and relevance. Stop sequence effectiveness: the effectiveness of the stop sequences in preventing the model from generating text beyond the desired point. Visualization plots. Text generation plot: a plot that visualizes the generated text, highlighting the stop sequences. Fine-tune parameters. None: this parameter is not fine-tunable. Uncertainty methods. None: there are no uncertainty methods associated with this parameter. Challenges and fixes. Challenge 1: the stop sequences may not always be effective in preventing the model from generating text beyond the desired point. Sample use case that resulted in Challenge 1: the model may continue to generate text even after encountering a stop sequence if the stop sequence is not sufficiently unique. Fixes to Challenge 1. Use more specific stop sequences that are less likely to be encountered in the generated text. Increase the number of stop sequences to improve the likelihood that one of the sequences will be encountered. Challenge 2: the model may generate text that is not relevant to the prompt or that is not coherent. Sample use case that resulted in Challenge 2: the model may generate text that is unrelated to the prompt or that is repetitive. Fixes to Challenge 2. Provide more context in the prompt to guide the model's generation. Use a more appropriate model for the task. Langchain Cohere RAG retrievers. Description: explain in detail. This retriever uses Cohere's embedding model to retrieve relevant documents from a collection based on a given query. It is part of Langchain's RAG retrieval augmented generation framework. Inputs. Input 1: explain in detail query, a natural language question or statement that the user wants to get information about. Input 2: explain in detail documents, a collection of text documents that the retriever can search through. These can be loaded from different sources like local files, databases, or web pages. Outputs. Output 1. Explain in detail relevant documents, a list of documents that are most relevant to the given query, ranked based on their similarity to the query's embedding. Output 2. Explain in detail embeddings for each document in the collection, which are numerical representations of the document's meaning. Steps. Step 1. Explain in detail. Generate embeddings. The retriever uses Cohere's embedding model to generate embeddings for the input query and each document in the collection. Step 2. Explain in detail similarity search. The retriever calculates the similarity between the query embedding and each document embedding. Documents with higher similarity scores are considered more relevant. Metrics. Metric 1. Explain in detail. Recall the proportion of relevant documents retrieved by the retriever. Metric 2. Explain in detail. Precision, the proportion of retrieved documents that are actually relevant. Visualization plots. Visualization plot 1. Explain in detail. Scatter plot. A scatter plot can visualize the relationship between query embedding and document embeddings in multidimensional space. Visualization plot 2. Explain in detail. Heat map. A heat map can show the similarity scores between the query and each document. Fine-tune parameters. Parameter 1. Explain in detail. Embedding model. The choice of embedding model, e.g. Cohere's embed extra large v2 can significantly impact the performance. Parameter 2. Explain in detail. Similarity metric. Different similarity metrics, e.g. cosine similarity. Euclidean distance can be used to measure the closeness between embeddings. Uncertainty methods. Uncertainty method 1. Explain in detail. Confidence scores. The retriever can provide confidence scores for each retrieved document based on its similarity score. Uncertainty method 2. Explain in detail. Ensemble methods. Using multiple embedding models and averaging their predictions can help reduce uncertainty. Challenges and fixes. Challenge 1. Explain in detail. Retrieval bias. The retriever might exhibit bias towards certain documents based on the embedding model's training data or the specific documents in the collection. Sample use case that resulted in challenge 1. If the collection contains more documents on a specific topic, e.g. technology, the retriever might be biased towards retrieving documents on that topic even for unrelated queries. Fixes to challenge 1. Data augmentation. Expanding the dataset with diverse documents can help mitigate bias. Pre-processing. Removing stop words and stemming words can reduce bias. Fine-tuning. Fine-tuning the embedding model on a dataset that reflects the desired distribution of documents can help. Challenge 2. Explain in detail. Cold starts. The retriever might struggle to find relevant documents for queries that are very different from the documents in the collection. Sample use case that resulted in challenge 2. If the collection contains documents about specific programming languages, the retriever might struggle to find relevant documents for a query about a completely different topic like history. Fixes to challenge 2. Expanding the collection, including documents on diverse topics, can help address cold starts. Query expansion. Expanding the query with related keywords can help retrieve more relevant documents. Knowledge base integration. Integrating a knowledge base with a broad range of information can help address cold starts. Langchain Cohere RAG retrievers. Cohere RAG retriever. Description. Cohere RAG retriever is a retrieval augmented generation RAG retriever that uses Cohere's large language model (LLM) for retrieval and generation. It combines the power of Cohere's advanced language understanding and generation capabilities with efficient retrieval techniques to provide highly relevant and contextually appropriate responses. Inputs. Text: the text that needs to be retrieved from. Query: the query that needs to be retrieved for. Outputs. Retrieved documents: the documents that are retrieved based on the query. Generated response: the generated response from the Cohere LLM based on the retrieved documents. And the query. Steps. Retrieval: the retriever uses Cohere's powerful language understanding capabilities to identify relevant documents from the given text based on the query. Generation: the retrieved documents are then passed to the Cohere LLM, which generates a response based on the retrieved documents and the query. Metrics. Retrieval accuracy: this metric measures the effectiveness of the retrieval process by evaluating the relevance of the retrieved documents to the query. Generation quality: this metric assesses the quality of the generated response, taking into account factors like coherence, factuality, and relevance to the query. Visualization plots. Retrieval visualization: this plot visualizes the retrieved documents and their relevance scores, highlighting the most relevant documents. Generation visualization: this plot analyzes the generated response, highlighting key entities and concepts from the retrieved documents. Fine-tune parameters. Retrieval model: this parameter allows users to fine-tune the retrieval model to optimize performance for specific use cases. Generation model: this parameter enables users to select a Cohere LLM model that best suits their needs. Temperature: this parameter controls the creativity and randomness of the generated response. Uncertainty methods. Confidence scores. Cohere RAG Retriever provides confidence scores for the retrieved documents and the generated response, indicating the level of certainty in the results. Explanation generation: the retriever can generate explanations for its retrieved documents and generated response, providing insight into its decision-making process. Challenges and fixes. Challenge 1: retrieval bias. The retriever might retrieve biased or irrelevant documents due to limitations in its language understanding capabilities. Sample use case that resulted in challenge 1: a query about a specific event might retrieve documents with biased information due to the presence of conflicting perspectives or different interpretations of the event. Fixes to challenge 1: fine-tuning the retrieval model using a diverse dataset and employing techniques to mitigate bias in the retrieved documents, such as incorporating multiple perspectives and sources of information. Challenge 2: generation quality. The generated response might not be coherent, factually accurate, or relevant to the query due to the limitations of the LLM. Sample use case that resulted in challenge 2: a query about a complex topic might lead to a generated response that is lacking coherence or factual accuracy. Fixes to challenge 2: fine-tuning the generation model using a dataset with high-quality responses, incorporating techniques for fact verification, and leveraging the model's ability to generate summaries or explanations to improve clarity and relevance. Langchain Cohere React Multi-Hop. Description: this chain combines Cohere's large language model (LLM) capabilities with React's multi-hop question answering framework. It leverages Cohere's ability to generate contextually relevant responses and React's ability to iteratively refine queries based on previous answers to answer complex multi-hop questions. Inputs. Question: a natural language question that requires multiple steps to answer. It could involve multiple entities, relationships, or require reasoning across different knowledge sources. Context: a list of text documents, articles, or any relevant information that provides context for the question. This could be a collection of web pages, knowledge base entries, or any other structured or unstructured text. Outputs. Answer: the final answer to the question, derived by iteratively refining the query and retrieving relevant information from the context. Intermediate queries: a list of intermediate queries generated by React during the multi-hop process. These queries represent the steps taken to reach the final answer, offering insight into the reasoning process. Steps. Initialize React: the chain starts by initializing React with the initial question and pay. Provided context. Generate Cohere response: React passes the current question to Cohere's LLM for response generation. Analyze response: React analyzes the response, extracting relevant entities, relationships, and potential follow-up questions. Refine query: React uses the extracted information to refine the original question. Generating new, more focused queries. Repeat steps 2 to 4. Steps 2 to 4 are repeated iteratively until React determines that a satisfactory answer has been found or a predefined maximum number of iterations is reached. Metrics. Accuracy: the percentage of correctly answered questions. Number of iterations: the average number of iterations required to answer a question. Query length: the average length of the generated queries. Visualization plots. Question-answer visualization: a visualization that displays the evolution of the question and the corresponding answers across each iteration, highlighting the refining process. Query refinement tree: a tree-like visualization that illustrates the branching of queries during the multi-hop process, showcasing the relationship between intermediate queries and their impact on the final answer. Fine-tune parameters. Cohere model: the specific Cohere LLM model used for response generation, e.g., command or generate. React threshold: the confidence threshold for React to determine if a satisfactory answer has been reached. Maximum iterations: the maximum number of iterations allowed for the multi-hop process. Uncertainty methods. Confidence scores: Cohere can provide confidence scores for its generated responses, which can be used to assess the uncertainty of the final answer. Query variance: the variation in the generated intermediate queries can indicate the level of uncertainty in the reasoning process. Challenges and fixes. Challenge 1: the LLM may generate irrelevant or inaccurate responses, leading to misleading queries and incorrect answers. Sample use case: a question about the capital of France might receive a response mentioning Paris, but also mentioning the capital of Spain, leading to a confused query about the capital of both countries. Fixes. Use a more specialized LLM. Employ a model trained on a specific domain or knowledge base to improve accuracy and relevance. Implement a filtering mechanism. Filter out irrelevant or inaccurate information from the LLM's responses before using them for query refinement. Challenge 2: the multi-hop process might get stuck in a loop, generating similar queries without converging on a final answer. Sample use case: a question about the lifespan of a specific species might lead to queries about its habitat, which might lead back to queries about its lifespan, creating a circular dependency. Fixes. Introduce query diversity. Encourage React to generate diverse queries by using different question formulation strategies or incorporating external knowledge sources. Implement a loop detection mechanism. Detect and break out of loops by comparing generated queries to previous ones and introducing new information or constraints. Challenge 3: the LLM might fail to understand complex relationships or infer connections between different entities, leading to incomplete or inaccurate answers. Sample use case: a question about the relationship between two historical figures might require understanding a complex chain of events and interactions, which the LLM might not be able to fully grasp. Fixes: use a knowledge-based LLM. Employ a model that leverages external knowledge bases or ontologies to facilitate reasoning and understanding of complex relationships. Incorporate domain-specific knowledge. Provide the LLM with additional contextual information or domain-specific knowledge that might be relevant to the question. Langchain Cohere React Multi-hop Parsing. Cohere Tools React Agent Output Parser. Description: Cohere Tools React Agent Output Parser is a parser designed to handle the output of a Cohere Tools React agent. This agent uses Cohere's large language model (LLM) to generate responses to user queries, potentially requiring multiple steps and interactions with external tools. This parser aims to extract meaningful information and structure the output for easy analysis in further processing. Inputs: Input 1: the raw output from the Cohere Tools React agent, which might include the agent's responses, actions taken, and any relevant information gathered during the execution. Input 2: optional configurations or parameters that might influence how the parser interprets the output, such as the expected format of the output or specific elements to focus on. Outputs: Output 1: a structured representation of the agent's responses, typically in a dictionary-like format, with key value pairs representing important aspects of the agent's output, like the final answer, the steps taken, or any errors encountered. Output 2: optionally, the parser might also generate metadata about the agent's execution, including information about the time taken, the resources used, or the agent's internal state. Steps: Step 1: parsing the raw output. The parser first processes the raw output from the Cohere Tools React agent, identifying and extracting relevant elements. This might involve using regular expressions, tokenization, or other techniques to identify and separate different parts of the output. Step 2: structuring the output. Once the relevant elements are identified, the parser constructs a structured representation of the output. This often involves grouping the information into meaningful categories, such as responses, actions, and errors, and then organizing them in a dictionary or other data structure. Metrics: Metric 1: accuracy. Evaluating the accuracy of the parsed output by comparing it to the expected result. This might involve comparing the extracted answer to the ground truth, checking for consistency in the identified actions, or verifying the reported errors. Metric 2: time efficiency. Measuring the time it takes for the parser to process the output. This metric is important for evaluating the performance of the parser, especially when dealing with large outputs. Visualization plots. Visualization plot 1: execution timeline. A visualization that represents the steps taken by the agent, the time spent on each step, and the flow of information between different components. This could be a Gantt chart, a flow chart, or a timeline diagram. Visualization plot 2: action flow. A visualization that shows the sequence of actions taken by the agent, including the input for each action, the output generated, and the impact of each action on the overall task. This could be a directed graph or a tree structure. Fine-tune parameters. Parameter 1: expected output format. The parser can be configured to expect a specific format for the agent's output, such as a JSON structure, a structured text format, or a predefined schema. This parameter can be used to tailor the parser to the specific use case. Parameter 2: filtering criteria. The parser can be configured to filter the output based on certain criteria, such as the type of actions to include, the level of detail required, or the specific elements to focus on. This can be used to control the complexity of the output and focus on the most relevant information. Uncertainty methods. Uncertainty method 1. Confidence score. The parser might include a confidence score for each extracted element, reflecting the level of certainty in the parsing process. This could be based on the probability of the extracted information being correct or the reliability of the source of the information. Uncertainty method 2. Error analysis. The parser might include an analysis of potential errors or ambiguities in the parsing process, highlighting any areas where the interpretation might be uncertain or incomplete. This could provide valuable insights into the reliability of the parsing process and guide future improvements. Challenges and fixes. Challenge 1. Handling variations in output format. The Cohere tool's React agent might generate output in different formats, depending on the task and the configuration of the agent. This can lead to challenges in parsing the output consistently and extracting the relevant information. Sample use case that resulted in challenge 1. The agent might generate a simple text response in one scenario, while in another it might output a JSON object with nested structures. Fixes to challenge 1. Implementing robust parsing mechanisms that can handle various output formats, including flexible regular expressions, tokenization techniques, and schema inference methods. Challenge 2. Identifying and resolving ambiguities. The output from the Cohere tool's React agent might contain ambiguous language or conflicting information. This can make it difficult to accurately interpret the output and extract the intended meaning. Sample use case that resulted in challenge 2. The agent might provide multiple answers with different levels of certainty, or might make conflicting statements about a particular topic. Fixes to challenge 2. Utilizing advanced natural language processing techniques, such as sentiment analysis, named entity recognition, and relationship extraction, to identify and resolve ambiguities in the output. Langchain Cohere React Multi-hop Agent. Create Cohere React Agent. Description: the Create Cohere React Agent function from the Langchain Cohere library is designed to construct a multi-hop reasoning agent leveraging Cohere's powerful language models for question answering and information retrieval. This agent is particularly useful for tasks where the answer to a query might require accessing and integrating information from multiple sources or steps. Inputs: query the user's question or request that the agent should attempt to answer. Retriever: an object responsible for retrieving relevant documents or text chunks from a specified knowledge base or corpus. This could be a simple vector database or a more sophisticated knowledge graph. LLM: a Cohere language model instance used for reasoning and generating responses. This model should be capable of understanding and processing the retrieved information to construct a coherent and informative answer. Max hops: the maximum number of steps or hops the agent should take to find the answer. This limits the depth of the reasoning process, helping to control the complexity of the search. Outputs: answer: the final generated answer to the user's query, compiled by the agent from the retrieved information and its reasoning process. Reasoning chain: a detailed breakdown of the steps taken by the agent to arrive at the answer. This includes the retrieved documents, the reasoning process applied to each document, and the final synthesis of the information. Steps: retrieval: the agent starts by using the provided retriever to identify documents or text chunks relevant to the query. Reasoning: for each retrieved document, the agent uses the Cohere language model LLM to analyze and reason about the information. This might involve extracting key facts, identifying relationships between concepts, or performing logical inferences. Integration: the agent combines the insights and information gathered from multiple documents, using the LLM to synthesize a coherent and comprehensive answer. Answer generation: finally, the agent generates a clear and concise answer to the user's query, incorporating the insights from the reasoning and integration steps. Metrics: accuracy: the percentage of queries where the agent provides a correct or relevant answer. Coherence: the quality and clarity of the generated answer, considering its logical flow and consistency with the retrieved information. Reasoning depth: the number of steps or hops the agent takes to find the answer, reflecting the complexity of the reasoning process. Retrieval effectiveness: the relevance of the documents retrieved by the agent, measured by metrics like precision and recall. Visualization plots: reasoning path: a visual representation of the agent's reasoning process, showcasing the steps taken and the connections between the retrieved documents. Information flow: a diagram illustrating the movement of information through the agent, highlighting the interactions between the retriever, LLM, and answer generator. Fine-tune parameters: temperature controls the randomness of the LLM's responses. Higher temperatures lead to more creative and unpredictable answers, while lower temperatures favor more conservative and predictable outputs. Top limits: the number of possible responses considered by the LLM at each step, potentially improving efficiency and reducing noise. Top: similar to top, but instead of limiting by count, it limits by the probability distribution of the LLM's output tokens. Uncertainty methods: confidence score: the agent can estimate the confidence level of its answer based on the LLM's output and the relevance of the retrieved documents. Multiple answers: the agent can generate multiple possible answers with varying confidence levels, allowing the user to choose the most suitable option. Challenges and fixes: Challenge 1: retrieval bias: the agent might retrieve biased or irrelevant documents if the retriever is not well tuned to the query and the knowledge base. Sample use case that resulted in Challenge 1: a query about the history of artificial intelligence might retrieve documents primarily focused on recent advancements, neglecting earlier milestones. Fixes to Challenge 1: improve the retriever's query processing and document scoring mechanisms. Enhance the knowledge base with more diverse and balanced information. Use query expansion techniques to broaden the search and increase the chances of retrieving relevant documents. Challenge 2: LLM hallucination: the agent might generate inaccurate or fabricated information due to the inherent uncertainty and limitations of language models. Sample use case that resulted in Challenge 2: the agent might incorrectly claim that a specific historical event occurred based on its interpretation of the retrieved documents. Fixes to Challenge 2: incorporate fact-checking mechanisms to verify the information generated by the LLM. Use techniques like grounding and reinforcement learning to improve the LLM's accuracy and reliability. Provide the agent with access to external sources of truth to cross-reference the generated information. Challenge 3: overly complex reasoning: the agent's reasoning process might become too convoluted or inefficient, leading to long processing times and potentially inaccurate results. Sample use case that resulted in Challenge 3: the agent might engage in unnecessary circular reasoning, repeatedly revisiting the same information without arriving at a conclusive answer. Fixes to Challenge 3: limit the number of hops or reasoning steps allowed by the agent. Use techniques like pruning and beam search to reduce the search space and prioritize the most promising reasoning paths. Implement early stopping mechanisms to terminate the reasoning process if it becomes unpredictable. Langchain Cohere React multi-hop parsing pass actions. Description: this component leverages Cohere's advanced language model to parse and understand complex multi-hop instructions within a React application. It takes natural language instructions, breaks them down into individual actions, and then executes those actions within the application state and UI. Inputs: natural language instructions. This is the primary input. A user-provided string describing the actions they want performed within the application. The instructions can be complex, involving multiple steps and logical dependencies between actions. Application state: the current state of the React application, encompassing the values of all components and variables. This context is crucial for parsing instructions that reference existing data or modify existing components. Outputs: list of action objects. The parser outputs a structured list of action objects, each representing a single step in the original instructions. These action objects contain information about the type of action, e.g., updating a variable, adding a component, triggering an event, the target component or variable to be modified, and any necessary parameters or data. Modified application state: the component updates the application state according to the parsed actions. This can involve modifying existing variables, adding new components, or changing the UI to reflect the user's instructions. Steps: instruction parsing. The natural language instructions are first parsed using Cohere's language model. The model identifies individual actions, their relationships, and any relevant context from the application state. Action mapping: each parsed action is mapped to a specific function or method within the React application that can execute the desired action. This mapping is based on a predefined dictionary or configuration that links natural language actions to their corresponding functions. Action execution: the mapped actions are then executed sequentially, modifying the application state and UI according to the user's instructions. Metrics: accuracy: this metric measures the percentage of instructions that are correctly understood and executed by the parser. Efficiency: this metric measures the time it takes to parse and execute the instructions. Balancing speed with accuracy. User satisfaction: this metric evaluates the user's experience with the instruction parser, considering the ease of use, clarity of feedback, and overall functionality. Visualization plots. Action flow diagram: this visualization presents a graphical representation of the parsed actions, showing their order of execution and any dependencies between them. State change log: this visualizes the changes to the application state resulting from the execution of past actions, highlighting the modified variables and components. Fine-tune parameters. Language model parameters. Cohere's language model can be fine-tuned for specific application domains or user vocabulary to improve the accuracy of instruction parsing. Action mapping configuration: the mapping between natural language actions and application functions can be tailored to optimize performance and handle domain-specific terminology. Uncertainty methods. Confidence scores: the parser can provide confidence scores for each parsed action, indicating the model's certainty about its interpretation. This allows developers to prioritize or review actions with lower confidence. Alternative interpretations: the parser can present multiple potential interpretations of ambiguous instructions, allowing users to choose the most appropriate action or provide clarification. Challenges and fixes. Challenge 1: handling ambiguous instructions. Instructions can sometimes be ambiguous or lack context, leading to misinterpretation. Sample use case that resulted in challenge 1. Add a new item to the list without specifying pay. List or the item's attributes. Fixes to challenge 1. Provide additional context, guide users to clarify their instructions by prompting for missing information or offering predefined options. Use context from the application state. Leverage the application's existing data to infer the intended target and attributes for the action. Implement a user confirmation step before executing the action. Present a summary or preview of the interpreted instruction to the user for validation. Challenge 2. Handling complex logic. Multi-hop instructions involving conditional statements or loops can be difficult to parse and execute correctly. Sample use case that resulted in challenge 2. If the total cost exceeds 100, apply a 10 discount. Otherwise, add a 5 surcharge. Fixes to challenge 2. Break down complex instructions. Decompose complex instructions into smaller, simpler actions that can be executed individually. Use flow control structures. Introduce conditional logic and loops into the action execution process to handle complex branching and repetition. Implement a virtual machine. Create a specialized virtual machine for executing parsed instructions, allowing for the manipulation of variables and execution of complex logic. Challenge 3. Handling dynamic UI changes. Parsing instructions can become challenging when the UI is dynamic and constantly changing, making it difficult to reference specific elements. Sample use case that resulted in challenge 3. Change the color of the button that appears after clicking the first button. Fixes to challenge 3. Use event listeners. Track UI events and update the parser's knowledge of the current UI state. Introduce a state management system. Employ a centralized state management system to maintain a consistent and up-to-date representation of the UI. Implement a UI exploration mechanism. Allow the parser to explore the UI and discover new elements and their properties as needed. Langchain Cohere React multi-hop parsing. Parsons where with prefixes. Description: this chain uses Cohere's large language model (LLM) to answer multi-hop questions, where the answer requires piecing together information from multiple sources. It's designed to handle more complex questions than a simple single-hop question. Inputs: question. The question to be answered, which can span multiple hops, requires piecing information together from different sources. Documents: a list of documents that potentially contain the answer to the question. These can be text, articles, or any other form of structured data. Outputs: answer: a string containing the final answer to the question. The answer is generated by the LLM and is based on the information gathered from the documents. Steps: the React multi-hop chain is initialized with the question and documents. It uses a Cohere LLM to process the question and the documents in a multi-hop fashion. This involves breaking down the question into smaller sub-questions, searching for relevant information in the documents, and then synthesizing the information into a coherent answer. The parsons where with prefixes step is used to extract relevant information from the documents using prefixes, which are keywords or phrases that identify specific pieces of information. This helps to ensure that the LLM focuses on the most relevant information in the documents. Metrics: accuracy. This can be measured by comparing the generated answer to a ground truth answer. It can be represented as a percentage of correct answers. Coherence: evaluating the readability and overall clarity of the generated answer. Visualization plots: question and answer. A plot showing the question and the corresponding answer generated by the chain. This can help to visualize the flow of information. Fine-tune parameters: Cohere model fine-tuning can be done on a Cohere model like Command or Extra Large to enhance its ability to answer questions in a specific domain or style. Temperature, a parameter of the LLM which controls the randomness of the output. A higher temperature can lead to more creative answers, while a lower temperature might produce more predictable answers. Uncertainty methods. Confidence score. The LLM can be used to generate a confidence score for the answer. A high confidence score indicates that the LLM is more certain about the answer, while a low confidence score suggests that the LLM is less certain. Probability distribution. The LLM can be used to generate a probability distribution over possible answers. This can help to identify the most likely answer, as well as other potential answers that the LLM considers plausible. Challenges and fixes. Challenge 1. Understanding complex relationships. When questions require the understanding of complex relationships between entities or concepts in the documents, the LLM may struggle to accurately extract and synthesize the information. Sample use case that resulted in Challenge 1. What is the relationship between the CEO of Google and the founder of Facebook? The LLM may have difficulty understanding the relationship between these individuals and providing a coherent answer. Fixes to Challenge 1. Train on a dataset of questions and answers specifically designed to address complex relationships between entities. Use a knowledge graph or other external knowledge source to provide the LLM with additional context about the entities and their relationships. Challenge 2. Handling ambiguity. The LLM may struggle when faced with ambiguous language in the question or the documents. Sample use case that resulted in Challenge 2. What is the average salary of a software engineer? The LLM might struggle to handle the ambiguity of software engineer. Different types of engineers. Various experience levels. Fixes to Challenge 2. Provide the LLM with more specific context or constraints to help it resolve the ambiguity. Use a question answering framework that can handle ambiguous queries, such as a framework that allows for multiple interpretations of the question and then provides the user with a list of possible answers. Langchain Cohere React multi-hop parsing. Parse citations. Description. Explain in detail. This pipeline leverages Langchain, Cohere, and React to enable multi-hop question answering with citation parsing. It utilizes a combination of techniques to provide comprehensive and well-supported answers. Input 1. Explain in detail a user question that requires accessing information from multiple sources. A collection of documents or articles containing relevant information. A comprehensive answer to the user's question. A list of citations supporting the provided answer, including sources and relevant passages. Step 1. Explain in detail the user question is processed and transformed into a series of sub-questions using Langchain's question answering capabilities. Each sub-question is then passed to Cohere's large language model LLM for retrieval of relevant information from the provided documents. Step 3. Explain in detail the retrieved information is then aggregated and processed to construct the complete answer. Step 4. Explain in detail the citations corresponding to the extracted information are identified and included in the output. Metric 1. Explain in detail accuracy of the generated answer is measured by comparing it to the ground truth or expert knowledge. Completeness of the citations is assessed by ensuring all relevant sources are included. Visualization. Plot 1. Explain in detail visualizations like heat maps or graphs can be used to represent the relationships between sub-questions and their corresponding information sources. Tree structures can visualize the multi-hop relationships between sub-questions and the final answer. Cohere's model parameters can be fine-tuned to improve its ability to answer specific types of questions or handle particular domains. Langchain's indexing and retrieval components can be customized to optimize performance for specific document formats and sizes. Confidence scores can be generated by the LLM to indicate its uncertainty about the answer and its reliability. Probabilistic methods can be used to quantify the likelihood of a specific answer given the available evidence. Handling complex relationships between multiple sources. A question might require information from multiple sources with overlapping or contradictory information. Implement a mechanism to detect and resolve inconsistencies between sources, possibly using a consensus-based approach or incorporating uncertainty estimation. Ensuring accurate and complete citation parsing. A source might contain multiple relevant passages, but only some are actually used to answer the question. Utilize advanced citation parsing algorithms that can identify and extract relevant passages from the document, possibly using techniques like named entity recognition or semantic similarity analysis. Challenge 3. Explain in detail maintaining coherence and fluency in the final answer. Sample use case that resulted in Challenge 3. The final answer might be composed of multiple pieces of information from different sources, leading to disjointed and incoherent writing. Fixes to Challenge 3 incorporate natural language processing (NLP) techniques to ensure fluency and coherence in the generated answer, possibly using techniques like summarization, paraphrasing, or sentence blending. Langchain Cohere React multi-hop parsing personified tool usage generation. Description: this pipeline uses Cohere's large language model LLM to parse multi-hop reasoning tasks, and then uses Langchain to execute the parsed instructions through the use of tools. This pipeline also handles the generation of code to interact with APIs using JSON formatted tool. Responses. Inputs. Input 1: a natural language prompt that requires multi-hop reasoning to arrive at the answer. For example, what is the capital of the country that borders the largest lake in the world? Outputs. Output 1: the final answer to the prompt. Output 2: the generated code to interact with the APIs based on the JSON formatted tool responses. Steps. Step 1: the input prompt is passed to the Cohere LLM to parse it into a series of logical steps and tool calls. Step 2: Langchain uses the parsed instructions to execute the tools and retrieve the required information. Step 3: the JSON formatted tool responses are analyzed, and code is generated to interact with APIs and extract the final answer. Metrics. Metric 1: accuracy of the final answer. This can be measured by comparing the generated answer to the ground truth. Metric 2: efficiency of the generated code in interacting with the APIs. This can be measured by the execution time and the number of API calls. Visualization plots. Visualization plot 1: a flowchart showing the multi-hop reasoning steps passed by the LLM. Visualization plot 2: a code visualization showing the generated code for interacting with the APIs. Fine-tune parameters. Parameter 1: the temperature parameter of the Cohere LLM, which controls the randomness of the generated text. Parameter 2: the maximum number of steps allowed in the multi-hop reasoning process. Uncertainty methods. Uncertainty method 1: the confidence score of the LLM in its parsed instructions. Uncertainty method 2: the number of times the tool execution failed due to incorrect parsing. Challenges and fixes. Challenge 1: the LLM may fail to correctly parse the multi-hop reasoning steps, leading to incorrect tool calls or an incomplete answer. Sample use case that resulted in challenge 1: a prompt with a complex chain of reasoning steps. Fixes to challenge 1. Fine-tune the LLM with more examples of multi-hop reasoning tasks. Increase the temperature parameter of the LLM to encourage more creative solutions. Challenge 2: the generated code might not be efficient or correctly interact with the APIs, leading to errors or unexpected behavior. Sample use case that resulted in challenge 2: a prompt that requires multiple tool calls with complex data structures. Fixes to challenge 2. Enhance the code generation component with more domain-specific knowledge. Use a robust code parsing and execution library to ensure accurate code execution. YAML. Langchain Cohere React Multi-Hop Prompt Convert to Documents. Description: this workflow utilizes Langchain and Cohere to perform multi-hop question answering. It converts raw text into documents suitable for analysis and then leverages Cohere's powerful language model for multi-hop reasoning. Inputs. Text: the input text in plain format. This could be a document, article, or any other text you want to analyze. Question: the question that you want to answer based on the provided text. Outputs. Answer: the answer to the question, generated through Cohere's multi-hop reasoning process. Reasoning chain: a detailed explanation of the reasoning steps taken by Cohere to arrive at the answer, outlining the relevant information extracted from the text. Steps. Text preprocessing: the input text is split into smaller units, typically sentences, to create a list of documents. This step might also involve cleaning the text by removing irrelevant characters or formatting. Embedding: each document is then embedded using a vector representation. This allows for efficient comparison and similarity calculation between documents. Cohere offers robust embedding models. Multi-hop reasoning: Cohere's language model iteratively processes the question and uses the document embeddings to find relevant information. This might involve multiple hops, where the model focuses on specific parts of the text and then uses the extracted information to further refine the search answer generation based on the information retrieved through the multi-hop process. Cohere generates a concise and informative answer to the question. Metrics. Accuracy: the percentage of questions answered correctly. Retrieval precision: the proportion of relevant documents retrieved during the reasoning process. Reasoning coherence: the clarity and logical flow of the reasoning chain presented to the user. Visualization plots. Reasoning chain visualization: a graphical representation of the multi-hop reasoning process, highlighting the connections between different parts of the text and the flow of reasoning. This allows for a deeper understanding of how Cohere arrived at the answer. Fine-tune parameters. Cohere model: you can fine-tune the specific Cohere language model to optimize performance for your specific domain or task. Embedding model: different embedding models can be chosen based on the nature of the input text and the question. Uncertainty methods. Confidence score: Cohere provides a confidence score for each answer, reflecting the model's certainty in its response. This can be used to identify cases where the answer might be less reliable. Attention weights: the model's attention weights during reasoning can provide insights into which parts of the text were most influential in generating the answer. Challenges and fixes. Challenge 1: handling complex or ambiguous questions that require multiple hops of reasoning. Sample use case that resulted in challenge 1: a question involving multiple entities in relationships might require several steps of information extraction and analysis. Fixes to challenge 1. Experimenting with different Cohere models designed for more complex reasoning tasks. Tuning the embedding model to better capture the nuances of relationships between entities. Challenge 2: ensuring the coherence and accuracy of the reasoning chain presented to the user. Sample use case that resulted in challenge 2: a long and complex reasoning chain might be difficult for a user to follow, potentially leading to confusion or misinterpretation. Fixes to challenge 2: implementing visualization techniques to make the reasoning chain more understandable, adding explanations to the reasoning steps, providing context and clarity for the user. Langchain Cohere React Multi-Hop Prompt Create Directly Answer Tool. Description: this tool uses Langchain, Cohere, and a React multi-hop prompt to create a tool that directly answers questions based on provided information. Inputs: question: the user's question that requires an answer. Documents: a list of documents containing relevant information. Outputs: answer: a direct answer to the user's question based on the provided documents. Steps: the tool first processes the user's question using the Langchain framework to extract keywords and concepts. The extracted keywords and concepts are used to search the provided documents for relevant information. The relevant information from the documents is then fed into the Cohere API, which generates a comprehensive answer using a multi-hop reasoning process. The multi-hop process involves the Cohere model iteratively analyzing the context and generating a more refined answer based on each step of the reasoning process. The final answer generated by Cohere is returned as the output of the tool. Metrics: accuracy measures how accurately the tool answers the user's question based on the provided documents. Coherence evaluates the flow and clarity of the generated answer, ensuring it is logical and well structured. Relevance determines the extent to which the generated answer is relevant to the user's question and the provided documents. Visualization plots: answer visualization displays the generated answer along with the corresponding supporting information from the documents. Reasoning path visualization visualizes the multi-hop reasoning process followed by the Cohere model to generate the answer. Fine-tune parameters: Cohere model size allows selecting different Cohere model sizes based on the complexity of the question and the desired level of reasoning. Temperature controls the creativity and randomness of the generated answer. Top K limits the number of possible words considered at each step of the reasoning process. Uncertainty methods: confidence score provides a numerical score indicating the confidence level of the generated answer. Evidence highlighting highlights the supporting information from the documents used to generate the answer. Challenges and fixes: Challenge 1: the tool might struggle to answer complex questions that require multi-step reasoning. Sample use case that resulted in challenge 1: a user asks a question that requires understanding several pieces of information from different documents, and the tool fails to connect the information effectively. Fixes to challenge 1: fine-tuning the Cohere model to handle more complex reasoning tasks, incorporating techniques like question decomposition and answer aggregation to break down complex questions into smaller steps. Challenge 2: the tool might generate factually incorrect answers due to hallucinations or biases in the underlying language model. Sample use case that resulted in challenge 2: the tool provides an incorrect answer to a question about historical events, potentially due to biases in the training data. Fixes to challenge 2: using a fact-checking mechanism to verify the accuracy of the generated answer. Incorporating external knowledge sources to supplement the information in the provided documents. Challenge 3: the tool might fail to answer questions that are not explicitly addressed in the provided documents. Sample use case that resulted in challenge 3: the user asks a question that requires inferring information from the documents, and the tool provides a generic or incomplete answer. Fixes to challenge 3. Implement a knowledge base or external API to access broader knowledge beyond the provided documents. Train the Cohere model on a larger and more diverse dataset to improve its ability to make inferences. Challenge 4. The tool might be prone to generating repetitive or overly generic answers. Sample use case that resulted in challenge 4. The tool repeatedly uses the same phrases or provides vague answers to similar questions. Fixes to challenge 4. Implement techniques like answer diversification to encourage the model to generate unique and informative answers. Use a reward function that penalizes repetitive or generic answers to encourage the model to provide more insightful responses. Langchain Cohere React Multi-hop Prompt. Description: this prompt allows users to perform multi-hop question answering by providing a series of questions that build upon each other. Each question can be answered using the previous question's answers as context. The prompt utilizes Cohere's large language model (LLM) for generating answers. Inputs: question: the user's initial question. Context: this can be a document, a set of documents, or a knowledge base that the prompt will use to answer the question. Max hops: the maximum number of questions the prompt can generate before reaching a final answer. Outputs: answer: the final answer to the user's question, which is generated through multiple hops. Hops: a list of all the questions and their corresponding answers that were generated during the multi-hop process. Steps: initialize: the prompt starts by receiving the user's question and context. First hop: the prompt uses Cohere's LLM to generate an answer to the user's initial question. Subsequent hops: the prompt uses the previous answer as context for the next question. This process continues until either a final answer is reached or the maximum number of hops is exceeded. Metrics: accuracy: the percentage of questions that are answered correctly. Hop efficiency: the average number of hops required to reach a final answer. Cohere API usage: the amount of API credits consumed by Cohere during the multi-hop process. Visualization plots: hop graph: a visualization that shows the flow of questions and answers throughout the multi-hop process. Answer quality: a visualization that shows the quality of each answer generated by the LLM, such as using a sentiment analysis score. Fine-tune parameters: temperature controls the randomness of the LLM's output. Higher values result in more creative and diverse answers. Top K limits the number of possible answers considered by the LLM. Lower values can improve accuracy but may limit creativity. Uncertainty methods: confidence score: the LLM can provide a confidence score for each answer, indicating its certainty about the answer's accuracy. Multiple answers: the LLM can provide multiple possible answers to a question, allowing the user to choose the most relevant one. Challenges and fixes: challenge 1: the LLM may generate incorrect answers, especially when dealing with complex or ambiguous questions. Sample use case that resulted in challenge 1: a user asks a question about a specific event, and the LLM generates an answer that is factually incorrect due to a misunderstanding of the question's context. Fixes to challenge 1: fine-tune the LLM on a specific dataset that is relevant to the type of questions being asked. Use a more specific prompt that provides more context to the LLM. Challenge 2: the LLM may struggle to understand and follow the user's train of thought during multi-hop question answering. Sample use case that resulted in challenge 2: a user asks a series of related questions, but the LLM fails to maintain the context of the previous questions and generates irrelevant answers. Fixes to challenge 2: Use a prompt that explicitly instructs the LLM to maintain context throughout the multi-hop process. Incorporate a memory component into the prompt that allows the LLM to store and access previous answers. Langchain Cohere React multi-hop prompt render intermediate steps. Description: explain in detail. This chain combines the capabilities of Langchain, Cohere, and React to build a multi-hop question answering system that leverages the power of large language models (LLMs) for complex information retrieval and reasoning. Inputs. Input 1. Explain in detail a user query or question that requires multiple steps of reasoning to answer. Input 2. Explain in detail a set of documents or knowledge bases that contain the information necessary to answer the query. Outputs. Output 1. Explain in detail the final answer to the user query generated by the LLM after multiple reasoning steps. Output 2. Explain in detail a list of intermediate steps taken by the LLM, detailing the reasoning process and how the final answer was derived. Steps. Step 1. Explain in detail. Langchain parses the user query, identifies key concepts and entities, and formulates a series of prompts for the LLM. Step 2. Explain in detail. Cohere's LLM is used to process each prompt and generate a response. The LLM may utilize different reasoning techniques like text summarization, question answering, or information extraction to extract relevant information from the documents. Step 3. Explain in detail. The responses from the LLM are analyzed by Langchain to identify key information and potential reasoning paths. Step 4. Explain in detail. Langchain dynamically constructs new prompts based on the previous LLM responses, iteratively refining the reasoning process until a final answer is reached. Step 5. Explain in detail. The final answer and the intermediate reasoning steps are presented to the user through a React interface. Metrics. Metric 1. Explain in detail. Accuracy measures how often the system provides the correct answer to user queries. Metric 2. Explain in detail. Reasoning time tracks the time it takes for the LLM to generate responses and the overall time required to complete the reasoning process. Visualization plots. Visualization plot 1. Explain in detail. A flowchart visualization that depicts the multi-hop reasoning steps taken by the LLM. Visualization plot 2. Explain in detail. A heat map visualization that highlights the importance of different concepts and entities in the documents based on the LLM's reasoning process. Fine-tune parameters. Parameter 1. Explain in detail. LLM model choice. Experimenting with different Cohere LLM models to find the best fit for the specific reasoning task. Parameter 2. Explain in detail. Prompt engineering. Optimizing the prompts used by Langchain to guide the LLM towards more effective reasoning. Uncertainty methods. Uncertainty method 1. Explain in detail. Confidence scores. The LLM can provide confidence scores for its responses, indicating its level of certainty in the generated answers. Uncertainty method 2. Explain in detail. Entropy measures. Analyzing the distribution of tokens in the LLM's responses to estimate the uncertainty associated with the reasoning process. Challenges and fixes. Challenge 1. Explain in detail. Handling complex queries. Complex queries may require multiple reasoning steps and necessitate the ability to handle nested dependencies between concepts. Sample use case that resulted in challenge 1. A query asking what is the capital of the country where the Eiffel Tower is located requires reasoning steps to first identify the country where the Eiffel Tower is located and then retrieve its capital. Fixes to challenge 1. Implement techniques like graph-based reasoning or iterative prompting to Handle complex dependencies and guide the LLM through multiple reasoning steps. Challenge 2. Explain in detail ambiguity and contextual interpretation LLMs may struggle with. Interpreting ambiguous phrases or understanding the context of the query. Sample use case that resulted in challenge 2. A query asking what is the meaning of life could lead to different interpretations depending on the user's background and context. Fixes to challenge 2. Provide additional context to the LLM through carefully crafted prompts. Leveraging external knowledge sources, or incorporating user feedback mechanisms to clarify ambiguities. Challenge 3. Explain in detail handling errors and inconsistency LLMs may generate incorrect or inconsistent answers during the reasoning process. Sample use case that resulted in challenge 3. The LLM might mistakenly identify the capital of France as Paris instead of Berlin due to errors in its knowledge base. Fixes to challenge 3. Implement error detection mechanisms to identify inconsistencies. Utilize external validation sources, or incorporate user feedback to correct errors. Challenge 4. Explain in detail bias and fairness LLMs may exhibit biases or generate responses that are unfair or discriminatory. Sample use case that resulted in challenge 4. The LLM might generate biased responses when answering queries about sensitive topics like race or gender. Fixes to challenge 4. Train the LLM on diverse and inclusive datasets. Implement bias mitigation techniques, or employ human oversight to ensure fairness in the responses. Challenge 5. Explain in detail scalability and efficiency. The system needs to be scalable to handle large amounts of data and efficiently process complex queries. Sample use case that resulted in challenge 5. When dealing with extensive knowledge bases or a high volume of user queries, the system's performance might degrade. Fixes to challenge 5. Optimize the underlying infrastructure. Utilize efficient data structures and algorithms, and explore techniques like distributed computing to improve scalability and efficiency. Langchain Cohere React multi-hop prompt render messages. Description: this component utilizes the capabilities of Langchain and Cohere to enable a multi-hop question answering system. It allows users to ask complex questions that require retrieving information from multiple sources and receive comprehensive and accurate answers. The React framework provides a user-friendly interface for interacting with the system. Inputs: question: a natural language question posed by the user. It can be any question that requires gathering information from multiple sources. Sources: a list of documents or URLs containing information relevant to the question. These sources can be articles, websites, or any other textual content. Outputs: answer: a comprehensive and accurate answer to the user's question, derived from the information gathered from the specified sources. Steps: pre-processing: the user's question is pre-processed by tokenization and stemming to remove unnecessary words and identify key terms. Source retrieval: the system searches through the provided sources to find documents relevant to the user's question. It uses techniques like keyword matching and semantic similarity to identify relevant information. Multi-hop reasoning: the system analyzes the retrieved documents to identify connections and relationships between different pieces of information. This involves identifying entities, relationships, and reasoning over the extracted facts. Answer generation: based on the multi-hop reasoning process, the system constructs a coherent and informative answer to the user's question. Metrics: accuracy measured by the percentage of correct answers to the user's questions. Coherence assessed by the clarity, relevance, and organization of the generated answer. Multi-hop reasoning accuracy evaluated by the system's ability to accurately identify connections and relationships between information from different sources. Visualization plots. Knowledge graph. This plot visualizes the relationships between different entities and concepts extracted from the source documents, providing a comprehensive overview of the information relevant to the question. Attention weights. This plot displays the attention weights assigned to different words and phrases in the source documents, highlighting the most important information for answering the question. Fine-tune parameters. Embedding model. The model used to convert text into numerical vectors, influencing the accuracy of semantic similarity calculations and source retrieval. Reasoning model. The model used to perform multi-hop reasoning and identify relationships between information, impacting the accuracy of answer generation. Uncertainty methods. Confidence score. The system provides a confidence score for each generated answer, indicating the level of certainty in its response. Source attribution. The system highlights the specific sources used to generate the answer, enabling users to verify the information and understand the reasoning process. Challenges and fixes. Challenge 1. Handling ambiguous questions or questions with multiple interpretations. Sample use case that resulted in challenge 1. The user asks what is the capital of France, but they might be asking about the capital city or the capital of the country. Fixes to challenge 1. Implement disambiguation techniques using contextual information and question analysis. Provide users with options or clarification prompts to resolve ambiguity. Challenge 2. Extracting accurate and relevant information from noisy or complex sources. Sample use case that resulted in challenge 2. A user asks a question about a specific event, and the source document contains information about the event but also includes irrelevant information. Fixes to challenge 2. Utilize advanced information extraction techniques to identify key entities, relationships, and events in the source documents. Implement filtering mechanisms to remove irrelevant information and focus on the relevant aspects. Challenge 3. Ensuring the coherence and fluency of the generated answers. Sample use case that resulted in challenge 3. The generated answer might be fragmented or lack logical flow, making it difficult for the user to understand. Fixes to challenge 3. Employ language modeling techniques to improve the fluency and coherence of the generated answers. Implement a human-in-the-loop approach to allow users to refine or edit the generated answers. Challenge 4. Handling questions that require common sense reasoning or knowledge beyond pay. Provided sources. Sample use case that resulted in challenge 4. The user asks a question about the relationship between two entities that are not explicitly mentioned in the provided sources. Fixes to challenge 4. Integrate external knowledge bases or common sense reasoning models to provide a broader context for the question. Explore using techniques like knowledge graph reasoning to make inferences and connect information from different sources. YAML. Langchain Cohere React Multi-Hop Prompt Render Observations. Description. This prompt aims to render observations from a multi-hop reasoning task using Langchain, Cohere, and React. The core functionality revolves around breaking down complex questions into simpler sub-questions, retrieving relevant information from multiple sources, and combining the retrieved information to answer the original question. Inputs. Question. The original question requiring multi-hop reasoning to be answered. Context. A list of documents or text chunks relevant to the question, which may include multiple sources. Outputs. Answer. The final answer to the original question, derived from the reasoning process. Reasoning steps. A step-by-step breakdown of the reasoning process. Outlining how the model derived the answer from the provided context. Steps. Question decomposition. The original question is broken down into a series of simpler sub-questions. Sub-question answering. Cohere is used to answer each sub-question individually, using relevant information from the provided context. Answer integration. The answers to the sub-questions are combined to construct the final answer to the original question. Metrics. Accuracy. The percentage of questions answered correctly. Reasoning length. The average number of steps taken to answer a question. Reasoning time. The average time taken to answer a question. Visualization plots. Reasoning path. A visualization of the reasoning process, showing the connections between sub-questions and the information retrieved from the context. Answer confidence. A visualization of the confidence scores assigned to each sub-question answer. Fine-tune parameters. Cohere model. The specific Cohere language model used for question answering. Reasoning strategy. The approach used to decompose the question and combine sub-question answers. Uncertainty methods. Confidence scoring. Assigning confidence scores to each sub-question answer to indicate the model's certainty. Reasoning path. Uncertainty. Estimating the uncertainty associated with each step in the reasoning process. Challenges and fixes. Challenge 1. Information overload. When the context contains too much information, the model may struggle to identify the most relevant pieces for each sub-question. Sample use case. When the context includes multiple documents on a complex topic, the model may struggle to extract the relevant information for a specific sub-question. Fixes. Context filtering. Implementing strategies to pre-filter the context and only provide the most relevant information to the model for each sub-question. Question refinement. Formulating more precise sub-questions to better guide the model towards relevant information. Challenge 2. Question ambiguity. If the question is ambiguous or poorly phrased, the model may misinterpret the intended meaning and produce incorrect answers. Sample use case. When the question is open-ended or uses vague language, the model may not be able to accurately understand the desired information. Fixes. Question clarification. Incorporating techniques to clarify ambiguous terms or rephrase the question for improved clarity. Question decomposition. Refinement. Breaking the question down into sub-questions that are more precise and less susceptible to ambiguity. Challenge 3. Reasoning complexity. When the question requires complex multi-hop reasoning, the model may struggle to maintain consistency and coherence across multiple steps. Sample use case. When the question involves multiple steps of inference and requires integrating information from different sources, the model may make errors in reasoning. Fixes. Reasoning step guidance. Providing explicit guidance to the model about the reasoning steps involved, such as specifying the order of sub-questions or providing intermediate results. Reasoning graph visualization. Utilizing visual representations of the reasoning process to aid in understanding and identifying errors. Langchain Cohere React multi-hop prompt render role. Description. This role represents a prompt that leverages Cohere's large language model (LLM) and Langchain's capabilities to construct the multi-hop reasoning chain for question answering. The prompt is designed to handle complex queries that require multiple steps of reasoning and information retrieval. Inputs. Query a user-provided question or statement that requires reasoning and information retrieval. Knowledge base. A collection of documents or text sources containing relevant information to answer the query. Contextual information. Any additional information, such as previous interactions or user preferences, that can assist in understanding the query. Outputs. Answer. The final answer to the user's query. generated by the multi-hop reasoning chain. Reasoning steps: a detailed explanation of the reasoning process, outlining the intermediate steps and decisions taken by the LLM. Confidence score: an indication of the LLM's confidence in the generated answer, based on factors like the coherence of the reasoning steps and the relevance of the retrieved information. Steps: query parsing: the prompt uses Langchain to parse the user's query and identify key entities, concepts, and relationships. Information retrieval: the LLM, guided by the parsed query, retrieves relevant information from the knowledge base. This might involve multiple iterations of retrieving, understanding, and refining the search based on previous results. Reasoning and inference: the LLM uses its reasoning capabilities to combine and analyze the retrieved information, making inferences and drawing conclusions to answer the query. Answer generation: the LLM synthesizes the reasoning process and information retrieved to generate a concise and informative answer. Metrics: accuracy: the percentage of queries answered correctly by the multi-hop reasoning chain. Coherence: the quality and consistency of the reasoning steps presented in the output. Retrieval effectiveness: the ability of the LLM to retrieve relevant information from the knowledge base. Visualization plots: reasoning path graph: a visual representation of the reasoning steps taken by the LLM, showing the connections between retrieved documents and inferences. Information retrieval flowchart: a visual diagram illustrating the information retrieval process, highlighting the key search terms and results obtained. Fine-tune parameters: temperature controls the randomness of the LLM's responses. A higher temperature leads to more creative and diverse outputs, while a lower temperature produces more predictable and focused answers. Cohere parameter: for controlling the size of the vocabulary considered during token generation. A lower value can lead to more focused and less diverse outputs, while a higher value allows for more possibilities. Uncertainty methods: confidence scoring: assigning a confidence score to the generated answer based on factors like the coherence of the reasoning steps and the relevance of the retrieved information. Probabilistic reasoning: utilizing probabilistic models to estimate the likelihood of different reasoning paths and inferences, providing a more nuanced representation of uncertainty. Challenges and fixes: Challenge 1: retrieval bias: the LLM might retrieve information that is biased towards specific perspectives or domains, leading to biased answers. Sample use case that resulted in Challenge 1: a query about the history of a particular event might retrieve sources that are primarily from a single viewpoint, neglecting other perspectives. Fixes to Challenge 1: incorporate diverse sources in the knowledge base, ensuring representation from various viewpoints. Use techniques like diversity sampling to ensure that retrieved information reflects different perspectives. Challenge 2: reasoning errors: the LLM might make reasoning errors, leading to incorrect inferences and inaccurate answers. Sample use case that resulted in Challenge 2: a query involving complex relationships between entities might lead the LLM to incorrectly connect entities or make incorrect inferences about their relationships. Fixes to Challenge 2: train the LLM on datasets that emphasize logical reasoning and inference skills. Employ techniques like chain of thought prompting to encourage the LLM to explicitly explain its reasoning process, allowing for easier error detection and correction. Challenge 3: contextual sensitivity: the LLM might struggle to incorporate contextual information into its reasoning, leading to irrelevant or incomplete answers. Sample use case that resulted in Challenge 3: a query about a specific event might require Knowledge of the user's previous interactions or preferences to generate a relevant answer. Fixes to challenge 3. Implement mechanisms to store and access contextual information during reasoning. Utilize techniques like prompt engineering to incorporate contextual information into the query itself, guiding the LLM's reasoning. Challenge 4. Data scarcity. The knowledge base might lack sufficient information on a specific topic, hindering the LLM's ability to answer the query. Sample use case that resulted in challenge 4. A query about a niche topic might not find enough relevant information in the knowledge base. Fixes to challenge 4. Expand the knowledge base by incorporating additional relevant documents and text sources. Utilize external APIs or knowledge graphs to retrieve information from external sources. Challenge 5. Ambiguity resolution. The LLM might struggle to resolve ambiguities in the query or retrieved information, leading to multiple possible interpretations and inaccurate answers. Sample use case that resulted in challenge 5. A query containing ambiguous terms might be interpreted in different ways by the LLM, resulting in different answers. Fixes to challenge 5. Implement techniques like disambiguation methods to identify and resolve ambiguities in the query and retrieved information. Train the LLM on datasets that emphasize ambiguity resolution and context sensitivity. YAML. Langchain Cohere React Multi-Hop Prompt Render Structured Preamble. Description. This prompt structure allows you to query a chain of multiple Cohere models, each designed to complete a specific task. To answer a question that requires multiple steps, the initial query is sent to the first model in the chain, which then generates a response based on the input. This response is then used as input for the next model in the chain, and the process continues until a final answer is produced. Inputs. Question. The question to be answered, which may require multiple steps to solve. Context. A set of documents or knowledge base information that can be used to help answer a question. Outputs. Final answer. The final answer to the question, which is produced after multiple hops through the chain of Cohere models. Intermediate responses. A list of responses generated by each model in the chain, providing insight into the reasoning process. Steps. The initial question is sent to the first Cohere model in the chain. The model analyzes the question and context, and generates an initial response. The response from the first model is then used as input for the next model in the chain, along with any relevant context. This process continues until the final model in the chain generates the final answer. Metrics. Accuracy. The percentage of questions that are answered correctly. Coherence. The quality of the generated text, in terms of readability, fluency, and relevance to the question. Efficiency. The speed at which the chain of models is able to process the question and generate an answer. Visualization plots. Flowchart. A visual representation of the chain of models and their interactions, highlighting the flow of information. Response timeline. A visualization of the time taken by each model in the chain to generate its response. Fine-tune parameters. Model weights. The weights of the Cohere models can be fine-tuned to improve performance on specific tasks or domains. Context window size. The size of the context window can be adjusted to allow the models to access more or less information. Uncertainty methods. Confidence scoring. Each model can provide a confidence score for its generated response, indicating its level of certainty about the answer. Ensemble modeling. Multiple models can be used to generate answers, and their responses can be combined to provide a more robust and reliable result. Challenges and fixes. Challenge 1. The models may struggle to understand complex questions that require multiple steps. To answer. Sample use case that resulted in Challenge 1. A question that requires multiple steps to answer, such as what is the capital of France? And what is its population? Fixes to Challenge 1. Use a more sophisticated chain of models, each designed to handle a specific aspect of the question. Provide more context to the models to help them understand the question and its requirements. Challenge 2. The models may generate responses that are not factually accurate. Sample use case that resulted in Challenge 2. A question about a specific historical event, where the model generates a response that contains inaccurate information. Fixes to Challenge 2. Train the models on a dataset of high-quality, factual information. Use techniques like fact-checking or verification to ensure the accuracy of the generated responses. Langchain Cohere React Multi-Hop Prompt Render Tool. Description: this tool facilitates multi-hop question answering using Cohere's large language model (LLM) within a React application. It leverages Langchain's capabilities to manage the chain of prompts and responses for effective question answering. Inputs. Question: the user's question that requires multiple steps to answer. Context: a collection of relevant documents or text that provide information to answer a question. Outputs. Answer: the final answer to the user's question generated by the LLM after multiple hops. Intermediate responses: the responses generated by the LLM at each hop of the question answering process. Steps. Pre-process: the input question and context are processed to ensure proper formatting and identify key entities for the LLM. First hop: the LLM receives the initial question and context and generates a response. Subsequent hops: based on the previous hop's response, the LLM generates follow-up questions or requests for specific information, iteratively refining the answer. Final response: once the LLM has gathered sufficient information, it produces the final answer to the user's question. Metrics. Accuracy evaluates the correctness of the final answer generated by the tool. Coherence measures the quality and fluency of the LLM's responses, ensuring they are clear and logical. Visualization plots. Question answering path: a visual representation of the multiple hops in the question answering process, showcasing the flow of information. Fine-tune parameters. Temperature controls the randomness of the LLM's responses, allowing for more creative or conservative answers. Top K limits the number of possible responses considered by the LLM at each step, influencing the diversity of answers. Uncertainty methods. Confidence scores: the LLM provides confidence scores for its responses, indicating its certainty in the generated answer. Multiple responses: the tool can generate multiple responses at each hop to provide a range of potential answers, highlighting uncertainty. Challenges and fixes. Challenge 1: the LLM may get stuck in a loop or generate irrelevant responses if the context is poorly structured or contains ambiguous information. Sample use case that resulted in Challenge 1: a user asks what is the capital of France, but the provided context includes text about Paris but doesn't explicitly state it's the capital. Fixes to Challenge 1: enhance the context pre-processing step to identify key entities in relationships. Use techniques like entity linking to connect information from the context with external knowledge sources. Challenge 2: the LLM might struggle with complex questions that require reasoning or inferencing across multiple hops. Sample use case that resulted in Challenge 2: a user asks what is the relationship between the author of Pride and Prejudice and the main character in The Lord of the Rings. Fixes to challenge to experiment with different prompt structures and chain strategies to guide the LLM through logical reasoning steps. Integrate external knowledge bases or tools for specific reasoning tasks. Langchain Cohere React Multi-Hop Prompt Render Tools. Description: this tool is designed to utilize the Cohere API for generating natural language responses based on multiple hops of reasoning. It leverages the Langchain framework to structure the multi-hop process, enabling the tool to gather information from multiple sources and synthesize a coherent response. This tool excels in scenarios demanding comprehensive understanding and integration of diverse information, particularly for applications like question answering, summarization, and content generation. Inputs: query the user's input question or request, serving as the initial prompt for the multi-hop reasoning process. Chain: the Langchain chain configuration, specifying the sequence of tools and prompts used for multi-hop reasoning. This chain orchestrates the retrieval and processing of information from diverse sources, potentially involving multiple rounds of interaction with the Cohere API and other tools. Outputs: response: the final generated response, encompassing the synthesized information from all hops of the reasoning process. This output is a natural language text, ideally conveying a comprehensive and coherent understanding of the user's query. Steps: the tool receives the user's query and the Langchain chain configuration. The tool parses the chain configuration and executes it, utilizing the Cohere API for natural language generation at each hop. The tool gathers and synthesizes information from multiple sources and rounds of interaction, following the specified chain logic. Finally, the tool constructs and returns a coherent natural language response based on the synthesized information. Metrics: response quality: the coherence, relevance, and accuracy of the generated response, assessed through subjective evaluation and potentially objective metrics like blue or rouge scores. Reasoning accuracy: the accuracy of the multi-hop reasoning process, measured by comparing the response's logical flow and information extraction against the ground truth or expected output. Visualization plots: multi-hop reasoning graph: a visualization of the chain execution, depicting the flow of information and interaction between different tools and sources. Response analysis: a visualization of the generated response's semantic structure, potentially using word clouds, topic modeling, or sentiment analysis tools to gain insights into the response's content. Fine-tune parameters: Cohere API key: this key grants access to the Cohere API for generating text, enabling the tool to perform multi-hop reasoning based on the provided chain configuration. Chain configuration: this parameter allows customization of the multi-hop reasoning process by specifying the sequence of tools and prompts used in the chain. Uncertainty methods: confidence scores: the tool can provide confidence scores for each hop of the reasoning process, indicating the certainty of the information extracted from each source. Temperature parameter: the Cohere API offers a temperature parameter, which can be adjusted to control the randomness and creativity of the generated text. By varying this parameter, the tool can explore different response variations and provide a measure of uncertainty in a generated response. Challenges and fixes: Challenge 1: handling complex or ambiguous queries that require multiple hops of reasoning in diverse information sources. Sample use case that resulted in Challenge 1: a user asks what was the average temperature in San Francisco last week, and what are the most popular restaurants in the city. This query necessitates retrieving temperature data for a specific time period and then identifying popular restaurants in the city. demanding multiple hops of reasoning and access to different data sources. Fixes to challenge 1 utilize a chain configuration that incorporates multiple tools for extracting information from relevant sources, such as a weather API and a restaurant review database. Design the chain logic to seamlessly integrate information from different sources and synthesize a coherent response. Challenge 2 ensuring response coherence and avoiding logical fallacies when synthesizing information from multiple sources. Sample use case that resulted in challenge 2 the chain retrieves information from a website claiming that the average temperature in San Francisco last week was 65 degrees Fahrenheit, while another source reports that the average temperature in the city last week was actually 60 degrees Fahrenheit. This discrepancy can lead to inconsistencies in the final response. Fixes to challenge 2 implement a mechanism for identifying and resolving conflicting information from different sources. This mechanism can involve using weighted averaging, incorporating confidence scores, or leveraging the Cohere API's contextual understanding to produce a coherent and logically consistent response. Challenge 3 managing the computational complexity and time requirements of multi-hop reasoning, especially for complex queries and lengthy chains. Sample use case that resulted in challenge 3 a user asks what are the key economic indicators of countries that are experiencing significant population growth, and how do these indicators differ from those of countries with declining populations? Requiring retrieval of economic data, population statistics, and analysis of the relationship between these variables. This process can involve a large number of hops, potentially leading to long execution times. Fixes to challenge 3 optimize the chain configuration for efficiency, potentially by streamlining the retrieval process, using pre-computed data, or employing caching mechanisms to reduce redundant computations. Explore techniques like parallel processing to accelerate the execution of multiple hops in a chain. Challenge 4 ensuring the reliability and trustworthiness of the information retrieved from different sources, especially in cases involving dynamic data or conflicting information. Sample use case that resulted in challenge 4 the chain relies on a website claiming that the average temperature in San Francisco last week was 65 degrees Fahrenheit, while the actual temperature data retrieved from a reputable weather API reveals a different average. This highlights the need for verifying information retrieved from potentially unreliable sources. Fixes to challenge 4 incorporate a mechanism for assessing the trustworthiness of different sources. This mechanism can involve using domain expertise, examining source credibility, analyzing the history of updates, or implementing cross-validation techniques to compare information from multiple sources. Langchain Cohere React Multi-Hop Prompt Render Tool Signature. Description: this tool utilizes the Cohere API to generate creative, engaging content for use in React applications. It leverages the multi-hop query capability within Cohere to generate multiple responses based on user input, providing a robust and dynamic interaction experience. Inputs. Input 1 user prompt or question. This input serves as the starting point for the multi-hop query. Input 2 optional context or background information. Providing additional context can enhance the quality and relevance of the generated responses. Outputs. Output 1 an array of strings representing the generated responses from Cohere. Each string corresponds to a separate response generated during the multi-hop query. Output 2 optional metadata from Cohere API, providing details about the generated responses, like their likelihood scores or tokens used. Steps. Step 1. The user prompt is formatted for the Cohere API based on the desired multi-hop configuration. This involves breaking down the prompt into multiple subprompts or questions. Step 2. The formatted prompt is sent to the Cohere API. The API processes the prompt and generates multiple responses based on the multi-hop query settings. Step 3. The generated responses are retrieved from the Cohere API and returned as an array of strings. Metrics. Metric 1. Cohere's response likelihood score. This metric provides an indication of the confidence level of the generated responses. Metric 2. Number of tokens used for each generated response. This metric can be used to monitor the resource consumption of the API call. Visualization plots. Visualization plot 1. A bar chart visualizing the likelihood scores of each generated response. Visualization plot 2. A heat map showing the distribution of tokens used for each response. Fine-tune parameters. Parameter 1. Temperature controls the creativity and randomness of the generated responses. Higher temperature values lead to more diverse and creative responses. Parameter 2. Max tokens sets the maximum number of tokens to be generated for each response. This parameter helps manage the length of the responses. Uncertainty methods. Uncertainty method 1. Confidence intervals for the likelihood scores of the generated responses. This can be used to assess the reliability of the responses. Uncertainty method 2. Using Cohere's top parameter to generate multiple responses and then evaluating the diversity and quality of the responses. Challenges and fixes. Challenge 1. Input prompts that are too complex or ambiguous can lead to incoherent or irrelevant responses. Sample use case that resulted in challenge 1. A user prompt requesting a list of historical events that happened in the year 2023 could result in a response of there were no historical events in the year 2023 due to the prompt being ambiguous about the time frame. Fixes to challenge 1. Clarifying the user prompt with specific keywords or time frames. 2. Providing additional context about the desired type of events. Challenge 2. The multi-hop query structure can sometimes lead to unexpected or unwanted responses if the sub-prompts are not properly sequenced or formatted. Sample use case that resulted in challenge 2. A prompt requesting the name of the first person to land on the moon, followed by their birth date, could result in an inaccurate answer if the sub-prompts are not properly ordered. Fixes to challenge 2. 1. Carefully designing and structuring the multi-hop query to ensure the flow of information is logical. 2. Thoroughly testing the query with different prompts and inputs to identify any potential issues. Langchain Cohere React Multi-Hop Prompt Render Type. Description: the React multi-hop prompt render type allows for multi-hop reasoning using Cohere's large language models (LLMs) within a Langchain application. It is specifically designed to handle prompts that require multiple steps of reasoning in information retrieval from various sources. Inputs: query the user's initial query or question that triggers the multi-hop reasoning process. Context: a list of documents or text chunks containing relevant information for answering the query. Each document can be from various sources, such as web pages, databases, or knowledge bases. Outputs: answer the final response generated by the LLM, which combines information from multiple hops and sources to answer the user's query. Steps: initialization: the user's query is first processed and potentially pre-processed to ensure it is in a suitable format for the LLM. Retrieval: the LLM uses the query to retrieve relevant documents or text chunks from the provided context. Reasoning: the LLM engages in multi-hop reasoning, considering the retrieved information from multiple documents to deduce a comprehensive answer. Finalization: the LLM produces a final response that synthesizes the information gathered during the reasoning process. Metrics. Retrieval accuracy measures how effectively the LLM retrieves relevant documents from the context. Reasoning accuracy assesses the quality of the LLM's reasoning process, considering the correctness and coherence of the answer. Answer quality evaluates the overall quality of the generated answer, focusing on its accuracy, clarity, and relevance to the user's query. Visualization plots. Retrieval path visualizes the documents retrieved by the LLM during the reasoning process, showcasing the path taken to arrive at the final answer. Fine-tune parameters. Temperature controls the randomness of the LLM's output. A higher temperature leads to more creative and unpredictable responses, while a lower temperature results in more deterministic and consistent answers. Top K determines the number of potential responses the LLM considers during generation. A higher value expands the search space, increasing potential creativity but potentially lowering accuracy. Top filters the potential responses based on their probability. A lower value emphasizes high probability responses, while a higher value allows for more diverse and potentially less accurate responses. Uncertainty methods. Confidence score. The LLM can assign a confidence score to its answer, indicating the degree of certainty in its response. Entropy, a measure of the diversity and uncertainty in the LLM's output distribution. Challenges and fixes. Challenge 1: hallucination. The LLM may generate incorrect or fabricated information, especially when dealing with incomplete or ambiguous data. Sample use case that resulted in challenge 1: the LLM may answer a question about a historical event incorrectly by fabricating details or dates. Fixes to challenge 1. Use reliable and verified sources of information. Train the LLM on a larger and more diverse dataset. Implement mechanisms to detect and mitigate hallucinations during the reasoning process. Challenge 2: bias. The LLM can exhibit biases based on its training data. Sample use case that resulted in challenge 2: the LLM may provide biased responses towards certain groups or demographics. Fixes to challenge 2. Use diverse and representative datasets for training. Implement bias detection and mitigation strategies during the training process. Regularly evaluate the LLM's outputs for bias. Challenge 3: lack of transparency. The reasoning process of the LLM can be opaque, making it challenging to understand how it arrived at a particular answer. Sample use case that resulted in challenge 3: it may be unclear which documents or pieces of information the LLM used to generate an answer. Fixes to challenge 3. Implement mechanisms to visualize the reasoning path, highlighting the retrieved documents and their relevance. Provide explanations for the LLM's responses, outlining the key reasoning steps. Challenge 4: difficulty in handling complex reasoning tasks. The LLM might struggle to handle multi-hop reasoning tasks involving multiple steps and intricate relationships between concepts. Sample use case that resulted in challenge 4: the LLM may fail to solve a complex problem involving multiple steps of reasoning and information retrieval. Fixes to challenge 4. Train the LLM on specific reasoning tasks using relevant datasets. Utilize techniques like question decomposition or reasoning chains to simplify complex tasks. Explore incorporating external reasoning systems or knowledge bases to augment the LLM's reasoning capabilities. Langchain Cohere Rerank. Description: explain in detail. The Langchain Cohere Rerank tool uses Cohere's reranking API to Reorder a list of documents or text snippets based on their relevance to a given query. Inputs. Input 1. Explain in detail. Query a string representing the user's question or search query. Input 2. Explain in detail. Documents. A list of strings representing the documents or text snippets to be re-ranked. Outputs. Output 1. Explain in detail. Re-ranked documents. A list of strings representing the documents or text snippets in the order of their relevance to the query. Output 2. Explain in detail. Scores. A list of floats representing the relevance scores for each document in the re-ranked documents list. Steps. Step 1. Explain in detail. The Langchain Cohere re-rank tool sends the query and the list of documents to Cohere's re-ranking API. Step 2. Explain in detail. The Cohere API uses a large language model (LLM) to understand the query and the documents and calculate a relevance score for each document. Step 3. Explain in detail. The API returns the documents in order of their relevance scores, with the most relevant document appearing first. Metrics. Metric 1. Explain in detail. Mean reciprocal rank (MRR). This metric measures the average reciprocal rank of the relevant document in the ranked list. A higher MRR indicates better ranking performance. Metric 2. Explain in detail. Precision. This metric measures the proportion of relevant documents within the top K ranked documents. A higher precision indicates better ranking performance. Visualization plots. Visualization plot 1. Explain in detail. A scatter plot showing the relevance scores of each document against their original ranking in the input list. This can help visualize the effectiveness of a re-ranking process. Visualization plot 2. Explain in detail. A bar chart showing the distribution of relevance scores for the re-ranked documents. This can help identify outliers and assess the overall quality of the ranking. Fine-tune parameters. Parameter 1. Explain in detail. Model. The name of the Cohere model to be used for re-ranking. Different models may have different performance characteristics and trade-offs between accuracy and speed. Parameter 2. Explain in detail. Top. The maximum number of documents to be returned in the re-ranked list. Uncertainty methods. Uncertainty method 1. Explain in detail. Cohere's re-ranking API does not directly provide uncertainty estimates for its predictions. However, it is possible to use techniques such as ensemble methods or Bayesian inference to estimate the uncertainty of the ranking. Uncertainty method 2. Explain in detail. Another approach is to analyze the difference in relevance scores between the top-ranked documents. A smaller difference in scores may indicate higher uncertainty in the ranking. Challenges and fixes. Challenge 1. Explain in detail. The re-ranking API may not always return accurate results, especially for complex or ambiguous queries. Sample use case that resulted in challenge 1. A user query with multiple interpretations or a set of documents with overlapping topics can lead to inaccurate re-ranking. Fixes to challenge 1. Use more specific queries. Provide context in the query, or use a more powerful re-ranking model. Challenge 2. Explain in detail. The re-ranking API can be computationally expensive for large document sets. Sample use case that resulted in challenge 2. Re-ranking thousands of documents can take a significant amount of time and resources. Fixes to challenge 2. Use a smaller subset of documents for re-ranking. Use a faster re-ranking model, or optimize the code for efficiency. Langchain Cohere re-rank. Cohere re-rank. Description. Cohere re-rank is a Langchain tool that leverages Cohere's re-ranking API to reorder a list of text results based on their relevance to a given query. It helps improve the quality of search results by prioritizing the most relevant information. Inputs. Query. The search query used to re-rank the results. Documents: a list of text documents to be re-ranked. Outputs: re-ranked documents: a list of documents reordered based on their relevance to the query. Steps: the tool takes the query and list of documents as input. It sends the query and documents to Cohere's re-ranking API. Cohere's API analyzes the query and documents, calculating a relevance score for each document. The API returns a list of documents sorted by their relevance scores. Metrics: re-ranking accuracy measured by comparing the ranking of documents before and after re-ranking. Higher accuracy indicates better relevance. Speed: the time taken by the tool to re-rank the documents. Visualization plots: a scatter plot showing the relevance scores of documents before and after re-ranking. Fine-tune parameters: model: the Cohere model used for re-ranking. Different models may have different performance characteristics. Top: the number of top-ranked documents to return. Uncertainty methods: Cohere's API does not provide confidence scores for the re-ranking results. Challenges and fixes: Challenge 1: Cohere's re-ranking API may not be available in all regions or may have usage limits. Sample use case that resulted in Challenge 1: trying to use the tool in a region where Cohere's API is not available. Fixes to Challenge 1: use a different re-ranking tool or ensure access to Cohere's API in the desired region. Challenge 2: the quality of re-ranking results can vary depending on the query and documents. Sample use case that resulted in Challenge 2: re-ranking documents that are very similar in content. Fixes to Challenge 2: consider pre-processing documents or using a different re-ranking model.